Hello. I think you can hear me. Yep. Hey, glad to see you here. Let me just, it's actually been a few weeks since I streamed, so let me just make sure I hide the right things and all that good stuff. Oh. All right, it's 11. It is time. All right. I wonder, is there a way to zoom in notes? Maybe we shouldn't use notes then. Also, the microphone is in the way of my typing, so let me raise it like this. Okay, that's much better. Okay, let's just use Vim. Happy to. Also, because with terminal we can zoom. All right, so normally on my stream I write code, but today I write notes. Hey, that rhymed. Okay, yeah, so welcome to the stream. I'm going to read the Swift concurrency, I guess, roadmap and proposal, and maybe revisit the manifesto that came out a few years ago. This will be the first time I read them for the most part. So you'll get some live actions, and maybe some live puzzling things out. I'll try to, I will try to understand everything. I am in no way like an expert in this domain. Like I haven't written a log, operating system log. Most of the time I deal with them. I dispatch something in a queue and then sling it back to some other queue when it's done. I understand all this stuff in conceptual level, but you may see me struggle, and that's part of the fun. Anyways, feel free to talk in the chat if you have suggestions or questions, anything like that. So the first challenge is, how do we find those proposals? And I assume they're all here somewhere. Concurrency. Where's the roadmap? I've only skimmed the manifesto. Can't say I'm too familiar with this in general, except to learn and struggle together. Exactly. All right. So here is the roadmap. Let's blow it up for you guys if you are watching my screen and not reading your own copy. Okay. And now this looks funny, a little funny on my iMac, but I will survive. All right. So how do I do this? Do I read it in silence, read it out loud? I guess I'll just read it out loud. Yeah, I guess like, in case you don't know, the data structures and just general like variables and stuff is not thread safe by default in Swift. So unless you wrap something with some atomic operations or use some logs, or manually dispatch some type, or always deal with some, like let's say always muted some type in a specific thread / queue, be a dispatch queue or operations. Things could go wrong. Like you access them in different places, so that's and the things could go wrong. And the second thing is we write callbacks in Swift today, and callbacks we all know and love them from the Objective-C days if you're old. And I guess in my mind, at least these two aspects will change after Swift introduced their concurrency stuff. And I also, based on these, I guess this is educated guess, because we've seen the manifesto, we've seen where big picture wise how this was thought about. This is even before ABI was a thing. So you've seen things like law of exclusivity, right? That's already enforced in places, and that's because it has ABI implications, if I remember correctly. So it has to be baked in early. That's not really, I guess, I don't know. I feel like that even though that is not related to concurrency, it will come back somehow, because like the way you check whether a variable is accessed exclusively by the law of exclusivity must be very similar to the way you check something is accessed in different threads in code, right? Like the way compiler does that. We'll see. Like I'm sorry. I just feel like it's good to start with some background. Or at least this is my personal background. So take that as a personal story if you already know all that. Anyways, there was the Swift manifesto, concurrency manifesto. I don't know how important it is to, I guess, be familiar with. I skimmed this yesterday to be like very transparent, and I feel like we don't need to revisit the manifesto at the moment. Maybe if we have more time, we will go back and read that. Okay. All right. Swift Concurrency Roadmap. Our goal is to make concurrent programming in Swift convenient, efficient, and safe. Safe is said last, so I assume safe is the most important thing. This document outlines a number of proposed additions and changes to the language to achieve this. Through the implementation of asynchronous functions and actors. Asynchronous functions, I think, is the part I said about callbacks. The fact that we have to write callbacks today manually with async await is a syntax trigger so that you don't have to. And actors. These additions will be proposed separately, but will be in many cases dependent on each other. This document serves to join them together, unlike a manifesto, which might describe multiple possible directions and in some cases unlikely directions. This document describes a single intended plan for tackling concurrencies in Swift. The end state of these changes will make asynchronous programming convenient and clear at the point of use. Okay, convenient and clear. So that's API design guideline stuff. Provide a standard set of language tools and unique techniques that Swift developers can follow, improve the performance of asynchronous code through better knowledge and compile time, and eliminate data races and deadlocks in the same way Swift eliminates memory unsafety. This last part is going to be... it's going to take some changes to the language. Yeah, I feel like the first 3 parts don't require a lot of semantic changes. You can build some of the stuff with libraries. You can, with small syntax additions. Anyways, the introduction of these features will span multiple Swift releases. Feature will be introduced in broadly 2 phases. The first phase introduces an async syntax and actor types. This will allow users to organize their code around actors in a way that will reduce but not eliminate data races. The second phase will enforce full actor isolation, eliminating data races along with a number of features to allow efficient and ergonomic interpolation of actors needed to make that isolation practical. Okay. Actor isolation. Yeah, I think I'm going to try to take some notes for my flashcards. I don't know what is... so far, everything looks pretty good. As a roadmap, this document does not go into the level of details as well as those proposals. It also discusses features for the second phase, but detailed proposals for this area will wait until the first phase is better defined. Okay, so I guess what we're going to have for now is just the first phase. There are a number of other isolated topics not covered in this document, such as asynchronous streams, parallel for loops, and distributed actors. Many of these features complement what is described in this roadmap and may be introduced at any point. Okay, so distributed actor, I mean, if I remember correctly, the idea of actor is you have this unit of code that's contained within itself, meaning if others try to access mutate things in it, the compiler will prevent it. And then the actors execute in their own little world, and you can send messages between actors, and that's how they communicate. And this way, you can scale your program. It's like a design pattern, essentially. You can scale your program to running in different threads, different CPUs, different processes. If it can be in different processes, then that means it can be on any number of machines, cores. Did I already say CPU? Yeah, and like even like specialized things like graphic cards and stuff like that, or TPUs, I guess. All right, motivating example. Recurring coding today are good. We tell people to protect their data with queues, yes, exactly, instead of locks, and return the result slow operation with asynchronous callbacks instead of blocking a thread. But doing these things manually is awful and error prone. Consider the following snippet of code that demonstrates these patterns. Okay, so we have a refresh player. It takes a callback. Okay, it dispatch a bunch of work into a refresh queue, and for each of the work, when it's done, we call complete. But it's not dispatching the calling the complete in a, it may be calling the complete in a different queue. We just have to know how all player is implemented, I guess. Okay, yeah, so all we did is doing this, which is, I assume, is not going to be a very expensive thingy, but anyways. So you call this guy, you'll get completion n number of times, n being the number of players. Okay, there's 3 observations we can make about this code. There's too much ceremony. This function is fundamentally just calling a function, transforming the result. assigning it to a property, we're transforming, okay, not number of times, we're just transforming the entire player's variable and give it to a callback. Anyways, there's not enough information to understand what exactly this do, because all player could give you like a list of players, and call this block for each of the inner lists, right? Anyways, but there's so much extra work involved with the queue and the completion handler that it's hard to see that. The extra ceremony makes it easy to introduce bugs. There's a direct assignment to the self.player property in the completion handler. What thread is that on exactly? What thread is this on? It is unclear. This is a potential data race. The callback may need to dispatch back to the right queue before it does assignment. Maybe this is handled by all players, but we cannot reason locally about whether the queue is thread safe. Okay, so we're gonna improve on this. Because like as I was reading the code, I also came up with the same question. Code is needlessly inefficient. Several function objects needs to be separately allocated. Several function objects. The closure being one. There's another closure that the queue takes, and then there's another closure that the all players function takes. References like self, which are used by these functions, must be copied into them. Yep, self went from all the way here, into here, and into here. And each time it's a copy. Yes. I mean, it's a reference, copy of the reference. Requiring data, reference counter operations. This function may run multiple times or not at all, often preventing compiler from avoiding these copies. Yep. And then these problems are inescapably tied together. Asynchronous callbacks are always eventually run exactly once, which means that they cannot participate in permanent reference cycles. Okay, so a callback. They cannot participate. Callbacks are always eventually run exactly once, which means they cannot participate in a permanent. I guess, yeah. Since Swift doesn't know this, it requires self to be explicit in the closures. Okay, that's what that means. Right. Some programmers respond to this by reflexively adding weak self and increasing both the runtime load and the ceremony of callbacks. Yes, because each time you use weak self, you need to check whether it's nil or not. Yeah, exactly. Since it must not handle the possibility of nil. Frequently, such function immediately return when self is nil, making it harder to reason about the correctness, since arbitrary amount of code may have been skipped. I guess this is a little vague, but I'm assuming this is when we're talking about multiple level of callbacks. You call this and this calls that, and at some point any of it can bail because self became nil. Then you end up having to analyze, the combo of each level being escaped, something like that. So the patterns shown here are good, but expressing them in Swift loses important structure and creates problems. The solution is to bring these patterns into the language. That will reduce boilerplate and let the language make the patterns safe, eliminating bugs and giving programmers the confidence to use concurrency more pervasively. Okay. It will also give us a chance to improve the performance of concurrency code. So my iOS developer brain needs to be calmed down a little, because like in iOS, like using concurrency is like almost used for optimization. You use it when you need to, but most of the time you don't think about it too much. Whenever you do, you kind of abstract it away and say hide it. Then you run something, it automatically, and as long as it's asynchronous, you just don't assume it's on the same queue, and you're good. Whether it's actually concurrent or not, you don't need to care until you run into a bug. But I think this concurrency stuff for the language is more towards. It obviously helps with those problems, but also it is a design pattern that's mostly used for programs that really needs to be running concurrently because of performance requirements and stuff like that. Yeah, anyways, I just like when I was reading the word pervasively, my brain, there's a little voice in my brain that's like, why? And then immediately another voice is like, just chill. Anyway. Hey, Dev Jack, stranger. We run a glorified JSON parser. We don't usually care about performance. Exactly. We care about 60 frames per second. That's our performance. So here's above code rewritten using our proposed new syntax. Refresh players, internal, okay, same. Async, nice. So player await all players. Map. Okay, so we went from this Swift. Oops. To see, this is the problem with big font is you don't really see them all together. So let's put them next to each other. Okay, so this function, instead of taking a callback, now it just declares itself to be asynchronous. And here we're calling, notice the queue is gone, right? So we're calling a function awaiting. So that means, I assume that means somewhere in here there's a asynchronous function, and we can guess from the original code that all players, right? All players was also taking a callback. Now it does not. Now it just asynchronously return a list of players, and then we just call map on that. So what really happened? I mean, these two are equivalent. So okay. So we await for this asynchronous function to finish, and then we call map on its result. And then we assign the result to players. There's no more references to self here, right? Nice. What else? Queue is gone, self is gone, callbacks are gone. Obviously, is one line. Okay. So things known about this example. Let's see how many I hit. Refresh player is now an async function. Check. All players is also an async function. Yep. Returns the result instead of passing it into a completion handler. Exactly. Because of this, we can use expression composition to call map functions directly on the returner. Yes. So I didn't think about this too much, but it is true that before this would have happened inside of a, but I think the composition happens here. I don't know. This is like a substantial difference. Well, players use itself. Wait, this chat is okay. The code style just don't require self dot on every access to local property. Yes, that is true. The await keyword appears before the expression calling all players, indicating that refresh players function can become suspended at this point. Await keyword appears before the expression calling all players, indicating that refresh player. Okay. Yep. Refresh player. So the fact that you have a await in your body means the whole thing can be suspended. Sure. Works similar to try. Await works similar to try in that it needs only appear once at the start of the expression. And then can be suspended, not directly in front of every call, and it can be suspended. Yes. So that was referring to the fact that instead of writing something like this, you could write something like this, right? Maybe like you can just coalesce the try at any part of the expression that is enough of an ancestor to cover all the throwing functions. So await is similar to this. So if these are all asynchronous, then instead of writing, you could write await, but you can also write await like this. Okay. The explicit self dot has been eliminated from property accesses because no escaping closure capturing self are required. Right. So in this whole thing, there's no more closures. Therefore, nothing will close on self. I like that. The accesses to the property all players and players are now cannot have data races. What? Well, this last part, I think there's not enough information to justify this yet, as we read, because this is async await is just a syntax trigger, right? I mean, obviously, you could look at it as a pure syntax trigger. I don't know how it's going to be implemented. So to understand how the last point, I should just read instead of second guessing the document. Yeah. To understand how the last point is achieved, we must step out a player and look at how queues are used to protect states. Okay. The original code was a method on a class that used refresh queue to protect its internal state. So you have a refresh queue here, and then you use it here. This is a common pattern, class with a private queue and some properties that should only be accessed on the queue. We replace this manual queue management with actor class. Actor class. You take a class, you become an actor. No, different kind. Actor class. Okay. It doesn't say anything about a queue. And this is where this is defined. Things to note about this example: declaring a class to be an actor is similar to giving a class a private queue and synchronizing all access to its private state through that queue. Private state. There's no private state, but I assume they mean these two gentlemen here. Because this synchronization is now understood by the compiler, you cannot forget to use queue to protect state. Yes, because there's no queue even doesn't even appear here, so there's nothing to forget. Compiler will ensure that you're running on the queue in the class's methods. Okay, so the entire method. And it will prevent you from accessing the state outside of those methods. Oh, now I see why they make them internal. This is very deliberate. Instead of making them private, because internal by default in today's world means, you know, you can access them elsewhere. But this sentence is saying, wait. This sentence is saying you cannot access these outside of these methods. So it is internal, but it's not. It's internal. Internal for an actor is not internal. Because of the compiler is responsible for doing this, it can be smarter about optimizing away synchronization, like when a method starts by calling an async function on a different actor. Right. Okay. Having this static relationship between the actor and its functions and properties lets us enforce the isolation of data on an actor and define away data races. We statically know whether we're in a context that can safely access an actor's properties, and if not, the compiler handles switching to that context. We statically know. How do we statically know? Well, you have to be a method of the same actor. If it's not, we're switching to that context. So if I'm, I guess, calling to a different actor, then we make that actor X. I don't know. Let's keep it going. Above, we've shown an actor class where you've got a tightly encapsulated set of properties and code. But the way we do UI programming today often spread code across a large number of classes that you're supposed to use from a single main thread. The main thread is a kind of an actor. It's a global actor, where we can mark classes and functions as being tied to the actor with an attribute. The compiler will let you reference this class from anywhere, but to actually call this method, you need to be on the UI actor. I think UI actor. So if it was appropriate for all the action of player refresh controller to be performed on a global UI actor, we would do it like this. Probably for all the actions of to be performed. So before this could be on any queue, and this makes it in the context of like where UI actor means main queue, it will happen on the main queue. Okay, so proposals for the first phase. I think from this we can spread out to different proposals. We'll be pitching the following proposals in the coming weeks in support of the first phase. Async await introduce a coroutine based async await model to Swift. Also, it's just before I move on, I noticed this like this number indicates how many times these links has been clicked. You can see the first link 200, second link 200, third link 190, and then it just like start degrading. So people started reading them, and then at some point they all exhaust and give up. We have 59 survivors. to the last link. Okay. Or maybe they got into a rabbit hole and kept clicking. Maybe there's some more stuff. Okay. Async await introduces a coroutine-based async await model to Swift. Functions will opt into being an async and can then await the result of other async functions, allowing async functions to be expressed in a model, a more natural straight line form. Straight line, yes. There's one line here. It's straight. It's not, yeah. Pitch here, proposal here. I guess we'll just read. Yeah, another choice we can make is whether to read the comments. I'm thinking we skim through the comments and see if anything is interesting, because I don't know how much comment is there, but I know there are a lot of proposals to go through. The task API and the structured concurrency. Live stats, yes. Task APIs and structured concurrency introduces the concept of task to the standard library. Ooh. This will cover API to create detached tasks. Task nurseries. Well, for dynamically creating child tasks. Nurseries. Well, in my world, that's called a factory, but I guess nursery is a word. And the mechanics for canceling and prioritization of tasks. So, dynamically creating child tasks. Awaiting values from multiple child tasks. Wait, I'm skipping. Mechanics for canceling and prioritizing child tasks. These are all from standard libraries. Okay. It also introduces scope-based mechanisms for awaiting values from multiple child tasks. Scope-based awaiting. Okay. Scope-based mechanism. I am trying to understand everything from just one sentence. I should make a note that when there are vagaries, we take a note and then move on, because I assume there's more details in these proposals. Whoops. Actors and actor isolation describes the actor model, which provides state isolation for concurrent programs. This provides the foundation for actor isolation, the mechanism through which potential data races will be eliminated. The first phase proposal will introduce partial actor isolation, leaving full isolation enforcements to a subsequent proposal. You see, to end COVID-19, we really need full isolation enforcement. Okay, that's why we need phase 2 right now. Concurrency okay, this is some long words. Concurrency interoperability. Concurrency interoperability with Objective-C introduces automated bridging between Swift's concurrency features, async functions, and the convention-based expression of I actually read this yesterday. Concurrency-based expression asynchronous function in Objective-C. This will allow existing asynchronous Objective-C APIs to be immediately usable with Swift's concurrency model and provide a alternative Swift translation of the API into an async function alongside the callback-based version. This is essentially, there's the client importer thing in the compiler, and it just you set a set of rules, and then whenever it sees a Objective-C signature, it will pattern match with the rules and rename the API. Sometimes the rule could just be, hey, if it's exactly matched this, then rename it to that. That's how you can use all the UIKit/foundation APIs, or at least early on, without like having an overlay for every single one of them. And I assume this is talking about whenever you have a callback that's properly named or properly identified, then we'll just rename it. Well, yeah, rename it when we import it to Object Swift, so that is now a async function. So expect UIKit and Foundation to interoperate interrupt with async await nicely. Anyways, async handlers introduce the ability to declare a synchronous actor function as an async handler. Okay, these functions behave externally like a synchronous function, but internally are handled like an asynchronous function. Whoa, what? These functions behave externally like a synchronous function. Okay, so you call it and it returns something. Done. Well, you call it, it executes blocks. And then when it's done, it returns on blocks. But internally are handled like a, okay, so this is, async handler is bridge between the actually escape patch from the asynchronous code. That makes sense. That makes sense. This will help one of my libraries. Anyways, yeah, I think I had to use a semaphore for this before. This allows traditional notification methods such as those on UI table view delegate to perform asynchronous operations without cumbersome setup. Okay. Actor isolation at the second phase. The goal for Swift to prevent data races on mutable state by default. The goal is for Swift to prevent data races on mutable state by default. The system through which this is achieved is called actor isolation. This is going to block the main thread all the time. I hope, yeah. Yeah, async handler. That's something to look out for. Yeah, there's a lot of potential abuse, right? Because people are comfortable with synchronous functions. So I can see like a beginner, just like whenever async code starts, they'll immediately use a grab async handler and kind of start blocking shit. The system is called actor isolation, both because actors are centrally important to how the system works. Okay, actor is centrally important. And because the system is centrally concerned with preventing actor protected state from being accessed outside of the actor. Okay, it's about preventing the protected state. Basically create a barrier, create access control. However, actor isolation restricts code even when actors aren't directly involved, when it is necessary for the correctness of the system under concurrency. Actor isolation restricts code even when actors aren't directly involved, when it is necessary for correctness of the system under concurrency. Okay, so this is saying, even though it's called actor isolation, there are some places where you may not see an actor and it's still working, but don't be surprised that is part of the actor isolation. Okay. We intend to introduce the feature described in this roadmap in two phases. First, by introducing the ability to create async functions and actors, and second, by enforcing full actor isolation. The basic idea of actor isolation is similar to the idea of exclusive access to memory. I bet this is a link to the law of exclusivity. Oh, part of it. Okay. and builds upon it. Swift's concurrency design aims to provide an easy-to-use and composable approach to safe concurrency by starting from the natural isolation of actors and then using ownership as a complementary tool. Ooh, see. This entire paragraph refers to the ownership manifesto. Well, no, I mean, not the entire paragraph, but this part is like the starting point. And then later, you can use owned and shared, those keywords, to, I guess, indicate whether something should be, I don't know, it's hard to see the full picture. The problem of actor, well, let's take a note. I'm using strong to indicate parts that I have question marks on. Problem of actor isolation reduces the problem of ensuring all the ordinary mutable memory. The problem of actor isolation reduces the problem of ensuring that all ordinary mutable memory is accessed only by a particular actor or task. Mutable memories accessed only by a particular actor or task. This in turn reduces to an analysis of how the memory is accessed and who can access it in the first place. We can categorize memory into a few groups. Property of an actor will be protected by the actor. So class, this game session is protected by what is it, refreshing control or some shit like that. Immutable memory, such as a let constant, local memory, var, local variable that's never captured, value component memory, property of a struct or enum case are already protected from databases. Immutable, because they're immutable, so it's read-only, it's not shared, it's read-only, it's shared but not mutable. Unsafe memory, such as arbitrary allocations referenced by unsafe mutable pointer, is associated with an unsafe abstraction. It's actively undesirable to try to enforce these abstractions to be used safely because these abstractions are meant to be usable by passing safe language rules. These abstractions are meant to be usable to bypass safe language rules when necessary. Instead, we have to trust the programmer to use them correctly. So unsafe stuff, unsafe pointers will become even more unsafe. Class component memories can also be accessed from any code that holds a reference to the class. This means that while the reference to the class may be protected by the actor, passing that reference between actors exposes its properties to data races. These also include references to class held with value types when these are passed between actors. Yes, because if you're holding a reference to a class, then it's just a address at the end of the day. So the address value itself, the variable that holds the address, is protected because it's in an actor. But the thing that the address points to is not protected because anything can point to it. The goal of full actor isolation is to ensure that these last two categorizations are protected by default. Okay, so I think I skipped this, right? Global memory, such as global or static variable, can be, in principle, be accessed by any code anywhere. So this is subject to data race. Yeah, right. So global memories and memories, I guess, passed by reference will be protected with full actor isolation. Okay, phase 1. Wow, it took us 15 minutes to go through this. And we're not there yet. So 1 hour. Holy. The first phase introduces safety benefits. Users will be able to protect global variables with global actors and to protect class members by converting them into actor classes. Frameworks that require access on a particular queue can define a global actor and default protocols to it. So global actors is user definable and assume UIKit will ship like a UIKit actor. Maybe like dispatch, the dispatch library can make their default queues all global actors. Number of import cases of actor isolation will be enforced in this stage. Okay, so my actor has an immutable variable, has a mutable array, and then has a synchronous function, and then adds a member to the array. Why isn't this just append? Oh, I don't know. Then we extend my actor, have an async function, and it adds another member to the array. It's allowed because it's its own property. It prints out the mutable. It takes another different actor of the same class, so we already know its definition. So we're allowed to access the immutable property of the other actor because it's immutable, so there's no data race, no potential for data race. Actor that cannot access others' mutable state. So we cannot mutate other actors' mutable array, even though it is internal, so you have visibility, but you cannot mutate it. Not only can you not mutate it, you cannot read from it. That is because that other actor may be mutating it. So here we're sharing. We cannot share for read or write. Okay. Asynchronous function can call async function on other actors. Await other async function, other actors self. Okay, so I guess because this function is full of errors, it doesn't matter that this is an infinite loop or infinite recursion. Okay. Oh, only asynchronous function can be called from outside of the actor. So we can't call this, which in our case explicitly mutate the internal state. Okay. This enforcement of non-source broking because actors and async functions are a new feature. Makes sense. Even after the introduction of actors, there will still exist the possibility of data race conditions through global variables and value reference types. Okay, here we go. The last 2 points. We're just revisiting. Okay, so we have a global variable of a list of arrays, and then we have another global variable, but this time we put it in a actor. How do you say that? Mark it with an actor queue? I don't know. This is what they mean about internal becoming private. Yeah. This is quite a bit to wrap my head around. Yeah, so because the hidden condition is there's a hidden condition which is like when can things race, right? So in this because I guess it's kind of they didn't want to elaborate on call out. Anyways, each time something is allowed, that means things cannot race, and it's an error means things could race. It's not explicitly spelled out here, so when you read this yourself again, maybe you can think through that way. It's like Why is this an error? What is the alternative? Why is the alternative racy? Okay. So there's a plain old class with a mutable string. Oh, mutable string. This is a weird way to initialize a string. Yeah. Wait, can you do that? Wait, what's in the playground? I mean, string is a collection, but does it conform to custom collection literal, string literal, expressible by string literal, by list? I forgot. I don't think this is a thing, is it? Yeah, maybe it's a typo. Okay. And then we have an actor. The actor rapid maybe. I'm not a rapper, but I can try. Actor class racy actor immutable class reference. Okay, so we have a reference to a plain old class. They have an async function. Okay, so this is dealing with those global variables. Here we just write plus equals safe access. It's safe because it's protected by global actor. Unsafe because it's not protected by global. Unprotected, yeah. So these are saying these are unprotected, but it doesn't mean it won't compile, right? So this is phase one. In phase one, this is valid code that will compile. It's just not safe. That's why I see. That's why the whole thing is called a racy actor. Let's see. So here we send the reference to the plain old class to another instance of the actor. And this is unprotected because, like I mentioned earlier, this is just passing a number, passing the address to the actual object. So allow access to unprotected shared mutable state. Yep. Take class. Yep. You can just take the class, muted it, and this could happen on any thread. In the first phase, we intend to preserve Swift's current default behavior. Global variables and class component memories are not protected from data races. Actor unsafe is therefore the default for this memory. Note that that's no worse than the current situation. Because this is the default of current Swift, enabling the first phase is non-source breaking. In the second phase, the introduction of further features will provide a full set of tools for working with fully isolated actors. The most important of these is the ability to restrict a type to be actor local. Actor local, a type. Wait, restrict. Okay. When a type is marked actor local, the compiler will prevent it from being accessed, being passed between actors. Instead, the reference would need to somehow be cloned, unshared before passed across a boundary. So there will be some type of syntax or semantics that says this is actor safe, and then after that point, the compiler will reject this line of code. Okay. I'm gonna copy this piece of code into my little note. I have a feeling this won't be used too much because this is phase 2 and we're not gonna have a lot about phase 2. So the default will be changed. Global variable will be required to be protected by global actor. Required. Oh. or marked actor safe. Actor unsafe. That makes much more sense. I was like, actor safe. So we can't have just plain global variables like this in phase 2. You either have to protect it with an actor, or you have to say this is unsafe, it's okay. Classes and types that contain certain class references will change from being actor unsafe by default to being actor local. Ooh. Okay, so essentially, this line of code won't compile anymore. That's pretty, yeah. This change in default will necessitate a source break and will need to be gated by a language mode. Okay, so we can turn on and off the actor phase 2 thingy. Code that touches a mutable global variable or shared class references across other actor boundaries fundamentally cannot be shown to be safe from data races. And we'll need change to ensure that and code written in the future is safe from data races. It is hoped that this source break will not be onerous. Explain that the use of global variable should be sparing, so people stop using today, help yourself. And most global variables can be protected by a global actor. As long as classes are not shared across actor boundaries, actor local annotations should not affect code within an actor. Right, so if you're just calling your own method manipulating stuff of your own stuff, then there's no need to, yeah. Okay. Where references must be passed across boundaries, like this, the language should make this obvious and the solutions simple. Okay. Promises. By further encouraging and simplifying the use of value types, the need to share classes across actors' boundaries should be reduced. Okay, there's some wishful thinking here. Use more structs, use less classes, people. The time between the two phases will give user opportunity to factor the code into actors and async functions, preparing for full isolation. So yeah, I mean these are. It's probably not just 100% wishful thinking, but there's always those bunch that, let's say, they care about shipping and they don't care about your language nerd shit. Unlike the pitches from the first phase, which will be pitched and proposed, the language features needed for the second phase will initially be raised for discussion on the evolution discussion section of the Swift forums. One of the main drivers for the two-phase approach is that wanting to give Swift users time to become accustomed to async functions and actors before moving to a full isolation model. It is expected that the experiences of porting large working code bases to actor and async functions will inform the functionality needed to enforce full actor isolation. Guilty. Yes. You see, I'm familiar with this mode because the team I'm on, they offer there's this type of thinking I'm guilty of that. This feedback should inform the discussion of features of the second phase. Features expected to be discussed and part of the second phase include introduce an actor local restriction on types. Actor local. So this is, if I have to guess, this will be implicit for every properties like this. So this is kind of like internal. You don't have to spell it out. If you don't, it's spelled out for you. Compiler support for guaranteed correct copy on write types via mutable if unique. Compiler support for guaranteed correct copy on write. Is that code generation? I mean, this is probably. I mean, this will be really ugly if you write like actor mutable if unique. What else can we say? Public. Yeah, I mean, that's quite a bunch of stuff. So, it's probably just a placeholder. Attributes to opt out of actor isolation. For example, where thread safety is being handled through other means. Okay, so we have glossaries of concepts. I don't know if let's go through it very quickly. One way to use a glossary is you keep it in mind, and then you go on and read other stuff. When you encounter some words you don't understand, you refer to a glossary, so look it up. So async function, already used to. Synchronous function, we are used to it. Thread, underlying concept of threads. Platform vary, but tend to share basic characteristics. True concurrency requires creating a platform thread. So yeah, platform thread, whatever that means. Like a Unix thread. By creating and running platform thread is expensive. C function calls and ordinary synchronous function calls require the use of a platform thread. True. And asynchronous function is a new kind of function which does not have to run completion. Which does not have to run to completion without interruption. Does not. So it can does not have to run to completion without completion. Interruption causes the function to be suspended. Okay. The point at which the async function may give up its thread and the suspension point. Okay, so you can suspend it. It's kind of a yield kind of stuff from Python, at least semantically. The task is an operation that runs asynchronously. All asynchronous functions run as part of some task. All asynchronous function runs as part of some task. Every single one is part of a task. When an asynchronous function call another asynchronous function, the call is still part of the same task, even if the task has to change actors. Okay, so you have an actor running in a TPU. You have another actor calling that actor, or another actor in your CPU calling that actor. The call, even though it triggers work in the TPU, it still belongs to the task that the CPU actor belongs to. However, this concurrency is bounded. A function that creates a child task must wait for it. A function that creates a child task must wait for it to end before returning. Okay. Wait, did I skip? Wait, I skipped. I stitched the first part of this bullet point and the second part of this bullet point together. You see, all this reading takes a toll. A task is the analog of a thread for asynchronous functions. Just like any C functions and ordinary synchronous Swift functions requires a platform thread, any asynchronous Swift functions require a task. See, I can pass the SAT. An async function can create a child task. Child task inherits some of the structure of the parent task, including its priority, but can run concurrently with it. Makes sense? Train my model in a million TPUs. However, this concurrency is bounded. A function that creates a child task must wait for it to end. Okay, train my model in a million TPUs. Go ahead, I will wait. A function wishes to initiate independent concurrent work that can outlast its spawning context uses a detached task program. rather than abandon. So you can spawn off a bunch of work and then detach the task, and then you can go away and the task can stay around or somehow something like that. So there must be a mechanism behind this that can reattach, right? Like you probably get a token or something, a PID. A partial task is a unit of schedulable work. When the concurrently executing function a task is suspended, that is the end of the partial task, and the new partial task is created to continue the overall task work. An executor, oh this is new, is a service which accepts the submission of partial tasks and arranges for some thread to run them. A async function that is currently running always knows the executor on which it's running. An executor is called exclusive if the partial task submitted to it will never be run concurrently. So an executor, if let's say a task is an analog of a thread for synchronous function, the executor is analog of a queue for synchronous function. You can put partial tasks onto them, and then I guess this is how you bridge the programming model with the underlying system, right? Like, you know, how does the task that I write in Swift get onto a TPU? Well, you have a special executor that knows how to do that. So when you write the task, you don't need to know where it's going to be run. Well, in theory. And then and when you're ready to run it, you hand it to the right executor. At that point, you will know where it will be run because you chose the executor, which will, materialize the task, I guess. An actor is an independent part of the program which can run code. It can only run one piece of code at a time. That is, it acts as an exclusive executor. Oh, an actor is an executor. Wait. Okay, maybe executor is not the level of abstraction that I was talking about. And the code it runs can execute concurrently with the code run by other actors. Okay. An actor can have protected state which can only be accessed by the actor. Protected state, right? Yeah, like your property. The system through which this is achieved is called actor isolation. Long-term goal is for Swift to guarantee actor isolation by default. An actor class is a reference type. Each instance of which is a separate actor. Its protected state is its instance property, and its actor functions are its instance method. A global actor is a global object. Its protected state and actor functions may be separated across many different types. They can be marked with an actor-specific attribute, which Swift can infer in many cases. All right. Ooh. Okay, that's 1 hour and some change of reading. I think I'm ready for a break. I don't know how much we can go through today, but we'll try another one. But for now, let's take like a 5-minute break. Okay. Let me I got 2 campaign messages. Oh wait, I realized I've been playing music. I tuned out for some of the second half. At least I finished the PR review. No problem, man. The nice thing about streaming, watching streams, is you don't have to pay full attention. It's not like a fully produced TV show. I can actually, if we're being real, I totally can cancel all my streaming service subscriptions and just keep like what's it called, the thing that doesn't give you Twitch ads and YouTube Premium. I just keep those two and I'm good, because like practically speaking, that's all I watch anyways. Fully produced, yeah, fully produced proposal reading. Instead of thinking about actors, we hire a bunch of actors, and then they act out how the memory and concurrency is handled. Wouldn't that be fun? Come on, Apple TV Plus. It's a free idea. Fully produced proposal reading. Damn. I mean, I've been thinking about this, right? Like this kind of thing come out in this cycle, in this time of year, probably because some of these work will be shipped by Dub 2021. The rehearsal of that will sure be fun. Imagine like the Swift core team just drop everything and just sit behind the director chair, and like, no, you're going to the wrong place. You're wearing the wrong costume. You are a exclusive actor. Oh, but you're what is it? Exclusive executor. What was I saying? Oh yeah. Some of these will be like the headline of Dub 2021. That's why they have to go through the introduction, discussion, proposal, and meanwhile, throughout this time they'll implement that, and then by Dub there will be a toolchain ready for you to download in Xcode 15. Holy shit, 15. And then you can use it. So that gives you an idea of like, well, there are two things. One is more meta than the other. That gives you an idea of how long these proposals take to fully go through, at least on the conservative estimate, right? They propose, probably not too soon, but can't be too late. They're putting some cushions. And the meta-analysis of this is, all this is like a big project management problem. Like you need a lot of orchestration behind the scenes. It's like, we're gonna do this next year. We have to put out the proposal. We have to implement the changes in the compiler, front end, back end. That meaning like the cell things, LLVM changes if necessary, changes in the standard library. And that's going to mobilize a whole bunch of people. And, I assume a lot of these ideas were thought throughout the years. But at some point, the core team have to gather together and focus and hash out all the details and finalize them into proposal. So that took a while. Who knows when that work started, right? But all of this is all tied to the deadline of Dub 2021. So, these people, all those work can't just happen independently. So there's a big puppet master. That's a kind of a not a great word, but there's a big orchestrator. That's like, let's go, like, let's all, hey, mark your calendar for starting from this month. We're gonna start on this work, and go. All these work streams goes. Okay, so what do we do next? I'm probably gonna order some lunch real quick. We can just go through that list, right? There is a proposals. Yes. We can read about async await. We can read about task, actor isolation, interoperability with J2C, async handler. There's no proposal here. So we have 4. Oh, let's read some of the comments. I guess this can be part of the break. Really great to see. Should it be marked with await? Let's see. Other async function. Should this be marked with await? I think this is no. Split 22 hours ago. Very cool. People don't mind too much, but I've moved in some discussion on a topic specific. Actors as an interface for heterogeneous computing. The idea of having actor isolated function running to actors-based data should be scaled to model the GPU kernel. I assume this from the beginning. Why is this even a question? I mean, have you read the manifesto? I mean, I don't blame people. There's so much stuff to learn. I think it would be very natural to express that async API where there's a good fit for an actor is an interesting question. To me, something that can be logically be an actor. That is, it fills a similar role as a language-supported actor without necessarily being a good fit with the language-supported actor features. The differences between a well-encapsulated actor class and an ordinary class with primary async function is very little. Just the semantic of extension methods. Yep. What? This document seems to already recommending anti-patterns as like using queues instead of logs and I have news for you, buddy. And it's not good. Oh, Dave Abraham. Posting on behalf of this guy and this guy. These two. Well, I don't know if he still works at Facebook. Some of the system programming folks we've been talking with would dispute whether that's good. The comment is, the basic patterns that we encourage for concurrency today are good. We tell people to protect their data. I mean, I think the good is disputable, but we definitely do this without a thought, without a second thought. They pointed out that aside from having lower absolute performance costs, that queue in a log-based system, they prevent that there are proven tools for deadlock detection and debugging. Yeah. So instead of make the programming language help you, you use some other tools to help you. Well, we think an async algorithm is probably essential for Swift. We also consider that this proposal may be ignoring the foundations that proven concurrent programming is built upon. By starting from the middle, without updating the memory and ownership models. Yeah, see, I thought ownership models. Anyways, choices in capital-based system programming may be baked into the language. I agree. Most of all, this is difficult because we do appreciate the obvious effort that's gone into these proposals on behalf of the whole Swift community. a massive document set is being exposed for the first time with very little prior opportunity to discuss the approach here in the forums. That makes it something of a fait accompli. Which nobody can reasonably challenge at the fundamental level without implying a huge cost to the proposers. Well, that's Apple for you. You've been in there before. Now you're out. Now you're one of us. One of us. Yeah, see, like that's what I mean. Like Dave Smith, he works on the runtime part of the library, the compiler, the language, I guess, not the compiler, runtime, language, runtime. Here's folks from, well, he doesn't count. Core team members. Okay, the counterpoints is very similar to the manifesto. Broad concerns without specifics. Ownership model can certainly help in some cases. Uniquely referenced entity is safe to pass from one actor to the next. If your claim is that we need to both introduce a full ownership model and move all code over to enable concurrency, you're going to need to make a strong case that such a model exists and can be widely. So essentially, this is saying like, instead of saying we didn't do some work, why don't you do the work? As for the memory model, we're intentionally attacking a low level, a level above the memory model with actors, intentionally. The low-level memory model can come later for use by experts. Okay. So that's this hark back to the one of the first words in the first sentences, or one of the last words in the first sentences. Blah 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 blah. Oh, this guy, by the way, I think he worked on Akka. I don't know how that's pronounced, but it's a Scala thing, I think. Powerful, reactive, concurrent, and distributed. Oh, with Scala? Yeah, it's for the JVM. Yeah, so this is the, I believe the Swift concurrency manifesto referenced this as well. This is where the actor thing is, I guess, proven, because like this is used in productions and it uses the actor model. And apparently that's what the core team liked when they wrote when they were, I guess, looking at the big pictures. What did he say? He's like, we're taking a step into the more permissive direction than other than runtime here in the design. In Akka style, one has to move the don't receive any other message until this returns. Do receive other messages until this returns and continue then. We build those in the library and they surface in Akka persistence where the persistence no longer. So he's saying like there are some details can still be fleshed out, like, you know, whether you can receive new messages while you're still running. Okay, so the comments actually are not as many. There aren't as many comments as I thought. Memory model internally attack a low level above. So Xiaodi is saying, just like ownership, law of exclusivity was baked into API stability before its well, memory ownership model is baked into the API before it's fully implemented. There should be some considerations discussed here as well, similar, even though we're not gonna implement or work through all of them. The intent of characterization to oh, I'm the first one to click it. Approach is better in several specific ways than outlined, but also needs to be carefully considered because there are trade-offs. Wait, he's speaking as if he's not part of the author of these. I'm sure he's pretty involved in higher level discussions. Maybe the details still he's new to them. Tim outlines a number of proposed additions that changes the language. Really great programming model which will lift the programming experience. Okay. We intend to. In my mind, I just clap this sentence into +1. First, introduce the ability to create async functions and actors. Second, oh, okay. Splitting it to two phases is extremely concerning. Majority of introducing actors to get rid of shared mutable state. Spawning bugs that go. Okay. This is the key to prevent safe model. Okay. So this point is like it's not safe enough. Actors will be adapted by the community very rapidly, and a lot of code will be written against the stage 1 of the design. Doing a hard source break in a subsequent release of the language is going to fracture the community and cause unnecessary problem. Okay, this classic theme of Chris is no language dialects. This is a very strong attitude held throughout the years. His personal attitude. The proposed stage 2 solution to memory isolation doesn't solve the general use case, which means that stage 2 will be less expressive than stage 1. This means that it might be very difficult to adopt even people who are willing to rewrite their code. Expressivity, yeah. Trait safety, expressiveness, pick one. The description above makes it sound like you're not interested in the extremely important case data structures that use fine-grained locking and lock-free data internally. While I agree that it's good to push programmers to just use actors to protect their own state, also it is important that we allow expert programmers to build powerful libraries that compose with actors correctly. I'm not an expert enough to see before this was mentioned that this is a problem. There is a simple solution here, which I have been discussing with John. Probably is a good summary of two issues. Oh. I will try to find sometime this weekend. That means right now. To write the reference type issues up, completely additive to the model proposed here, I'll resolve the concerns above. Is well received, we can talk about globals. Oh, okay. Try to review the initial proposal drafting details, provide around. Okay, so that's the comment. Yeah, let's move on to the next one. Okay, let's read about async await. Coroutine based. What does that mean? Oh, it's just the Wikipedia. Okay. Coroutine accumulates programming components general subroutines for non-preventive multitasking. Yeah, we know that. I mean, I don't understand coroutine. Well, let's see. I don't know how to implement coroutine in the operating system in the precise details. Nah, I don't know. I don't know if that's important enough. Okay, async await. Wait, increase. All right. Okay, so it's already implemented in the latest snapshot with this flag. Modern Swift development involves a lot of asynchronous or async programming closures and completion handlers, but these APIs are hard to use. It gets particularly problematic when many asynchronous operations are used, error handling is required, or control flow between asynchronous calls gets complicated. This proposal describes a language extension to make this a lot more natural and less error-prone. This language introduces a coroutine model to Swift. Functions can opt into being async, allowing the programmer to compose complex logic involving asynchronous operations using the normal control flow mechanisms. The compiler is responsible for translating an asynchronous function into an appropriate set of closures and state machines. Okay, so coroutine model is the interesting thing, the new thing. Oh, the links to the same Wikipedia article. Is there a way to hide this bar? I guess I can do. Oh, implementation for Swift. Oh, that's a library. Anyways, not this one. This proposal defines a so another thing I notice is that it's just a translation, right? This is async await. A lot of people think of this whole this whole set of language changes as async await. That's actually so wrong, because async await is just another way to write callbacks, right? The interesting thing is the actors, the executors, and the coroutines and things like that. This proposal defines the semantics of asynchronous functions. However, it does not provide concurrency exactly. So it's a semantic. So meaning it's kind of a control flow thing. It doesn't mean anything. Just like when you use callback, it doesn't mean anything. It's asynchronous. It's an interface thing. That is covered by a separate proposal to introduce structured concurrency, which associate async functions with concurrently executing tasks and provide APIs for creating, queuing, and canceling tasks. The proposal draws some inspirations, and mostly from the motivation section, from an earlier proposal written by Latner, Groff, available here. That proposal itself is derived from a proposal written by Oleg Andreev, available here. It has been significantly rewritten again, and many details have changed, but the core idea of asynchronous function have remained the same. Okay. Completion handlers are bad. Async function with explicit callbacks, also called completion handlers, has many problems, which we will explore below. We propose to address these problems by introducing the async function into the language. Async functions will allow asynchronous code to be written as straight line code. They also allow the implementation to directly reason about the execution pattern of the code, allowing callbacks to run for far more efficiently. Efficient, okay. Pyramid of Doom, we all know this. The Pyramid of Doom makes it difficult to read and keep track of where the code is running. In addition, having to use a stack of closures leads to many second-order effects that we will discuss next. I remember there's a bullet point that I want to resolve. Here, okay. Okay, so Pyramid of Doom is bad. Error handling is difficult and verbose. Switch to, but callback-based interface does not derive a benefit from it. Right. So you can throw an error and catch it, but you can't do that if your function is async, because the way you return a value is through a callback. The callback itself can throw. Well, let's read the example. You load some resources. If the resource doesn't exist, you complete with an error. Ah, okay, that's what they mean. Yeah, to propagate the error, I guess naturally you include it as part of your completion block, and you do this at multiple levels. And you call the same completion block at each level. And each one can return their own error. That's made better if you include a result. Because, okay, here you can use a map. Yes. Result make the code shorter, but closure nesting problem remains. Okay, so this pattern is improved by result. Makes sense. But this pattern is not. See, that's why async await is just a syntax thing. Anyways, conditional execution is hard and error prone. Okay, I think this is related to my point here. Conditionally executed a async function is a huge pain. For example, suppose we need a swizzle. We need to swizzle an image after obtaining it, but we sometimes have to make an asynchronous call to decode the image before we can swizzle. Oh. Perhaps the best approach to structuring this function is to write the swizzling code in a helper coroutine closure that is conditionally captured in a completion handler like this. There's a swizzle thing. If it has the profile picture swizzle, otherwise you call a async function. When it completes, you swizzle. This pattern inverts the natural top-down organization of the function. The code that will execute in the second half of the function must appear before the part that executes in the first half. In addition to restructuring the entire function, we must now think carefully about capturing the continuation closure. Because the closure is used in a completion handler, the problem worsens as the number of conditionally executed async functions grows, yielding what is essentially an inverted pyramid of doom. Yeah. Many mistakes are easy to make. It is quite easy to build the asynchronous operation early by simply returning without calling the correct completion handler block. When forgotten, the issue is very hard to debug. This is a very practical thing. A lot of bugs come up because we can forget. We can simply, we just like, because not calling completion block is not a compiler error. So, yeah, it's very hard. I've dealt with code where there are multiple level of completion handlers, and the inner block has access to all of them, and it may conditionally call one or any of them, and that's just dealing with that code is soul draining. When you do remember to call the block, you can still forget to return after that. Yes. Yes. Nodders. Thankfully, the guard syntax protects against forgetting to return to some degree, but is not always relevant, okay? Because completion blocks are awkward, too many APIs are defined synchronously. This is hard to quantify, but the author believe that awkwardness of defining and using asynchronous APIs leads to many APIs being defined with apparently asynchronous behavior, even when they can block. This can lead to problematic performance and responsiveness for in UI applications. Spinning cursor. It can also lead to the definition of APIs cannot be used. Oh yeah, well that's maybe there are some bad APIs, but I'm sure it exists in private forms in applications. Okay, so we propose async await. Yay! Asynchronous functions, often known as async await, allows asynchronous code to be written as if it were straight line synchronous code. This immediately addresses many of the problems described above by allowing programmers to make full use of the same language constructs that are available to synchronous code. The use of async await also naturally preserves the semantic structure of the code, providing information necessary for at least 3 cross-cutting improvements to the language. 1. Better performance for asynchronous code. Better performance. Because you don't have to create an actual block object and copying the self. I think that was mentioned in the roadmap. Number 2, better tooling to provide a more consistent experience while debugging, profiling, and exploring code. Tools, okay. Number 3, a foundation for future concurrency features like task priority and cancellation. This example from the prior section demonstrates how async await drastically simplify async code. Okay, so you just define all these inner functions as outer asynchronous functions, and then you just call them line by line. Straight line. Call them in a straight line. You load the resource, wait for it. You get it here, you load the resource here, bring it here, use that here. Okay. Many descriptions of async await discuss it through a common implementation mechanism, a compiler pass which divides the function into multiple components. Okay. This is important at a lower level of abstraction in order to understand how the machine is operating, but at a high level, we'd like to encourage you to ignore it. Instead, think of an asynchronous function as an ordinary function that has the special power to give up its thread. Asynchronous functions don't typically use this power directly. Instead, they make calls. And sometimes these calls will require them to give up their thread and wait for something to happen. When that thing is complete, the function will resume executing again. That makes sense. That's a very natural way to think about it. I would argue the other way that they mentioned earlier is a lesser known way to think about async await. Just imagine like all the JavaScript users thinking in terms of how their interpreter is splitting up their functions into multiple sections, components. Having a hard time thinking about that. The analog with synchronous function is very strong. A synchronous function can make a call. When it does, the function immediately waits for the cell to complete. Once it completes, control returns to the function and pick up where it left off. The same thing is true with the asynchronous function. It can make call as usual, and when it does, it normally immediately waits for the call to complete. Once it completes, the control returns to the function and it picks up where it was. The only difference is that synchronous function get to take full advantage of the thread and its stack, where asynchronous functions are able to completely give up that stack and use their own. Separate storage. This additional power gives asynchronous function this additional power given to asynchronous function has some implementation cost, but we can reduce that quite a bit by designing holistically around it. Because asynchronous function must be able to abandon their thread, and synchronous function don't know how to abandon a thread, a synchronous function cannot ordinarily call an asynchronous function. Okay, so async functions can only be called by async function. The async function would only be able to give up the part of the thread it occupied, and if it tried, its synchronous caller would treat it as a return and try to pick up where it was, only without a return value. So instead of returning the value, you return the entire original state where before the async function was called. The only way to make this work in general would be to block the entire thread until this asynchronous function was resumed and completed. And that would completely defeat the purpose of asynchronous functions, as well as having nasty systematic effects. Okay. In contrast, an asynchronous function can call either synchronous or asynchronous functions. While it's called a synchronous function, of course, it cannot give up its thread. In fact, asynchronous functions never just spontaneously give up their thread. They only give up a thread when they reach what's called a suspension point, marked by a wait. Okay, a wait marks a suspension point. A suspension point can occur directly within a function, or it can occur with another asynchronous function that the function calls. But in either case, the function and all of its asynchronous callers spontaneously abandon the thread. Right. So whenever a asynchronous function starts to execute, all their parent, all callers abandon their thread. In practice, async functions are compiled to not depend on the thread during an asynchronous call. Okay, so that only the innermost function needs to do any extra work. When the control return to a actually, let me take that. In practice, asynchronous functions are compiled to not depend on the thread during async call. Okay. Yeah, depend on is kind of unclear to me. Okay. When control returns to an asynchronous function, it picks up exactly where it was, and that doesn't necessarily mean that it'll be running on the exact same thread it was before. Oh, that's what depend on means. Okay, I got it. Interesting. So the compiler could put you on a different thread when the when your await finishes. Because the language doesn't guarantee that after a suspension, right? In this design, threads are mostly an implementation mechanism, not part of the intended interface to concurrency. However, many asynchronous functions are not just asynchronous. They're also associated with special actors, which are the subject of a separate proposal, and they've always proposed to run as part of that actor. Okay, so we have an actor, as we saw earlier. Then there's some guarantee, right? The actor will run in a certain context, and everything in there will run in that context. Swift does guarantee that such function will in fact return to their actors to finish executing. Accordingly, libraries that use threads directly for state isolation, for example, by creating their own threads and scheduling tasks sequentially onto them, should generally model these threads as actors in Swift in order to allow these basic language guarantees to function properly. So this is saying, yes, you can still use your P threads, but when you do that, when you do that, you don't get these language features, and also when you do that, you have to use unsafe pointers, and their thing can run wild anyways. That's neat. Yeah. Suspension points. Yes, I've highlighted suspension points. Okay. The suspense. A suspension point is a point in the execution of an async function where it has to give up its thread, right? Suspension points are always associated with some deterministic, syntactically explicit event in the function. They're never hidden or asynchronous forms of the function's perspective. They're never hidden or asynchronous from the function's perspective. That's a little mind-bending. Suspension point being asynchronous, luckily for us, is never asynchronous. So the detailed language design will describe several different operations as suspension points. The most important one is called an async function. Is a call to an async function associated with a different execution context. It is important that suspension points are only associated with explicit operations. In fact, it's so important that this proposal requires that the calls that might suspend be enclosed in an await expression, just like a call that might throw is enclosed in a try expression. This allows Swift's precedence of using try expression to cover calls functions that can be throw functions. Marking suspension point is particularly important because suspensions interrupt atomicity. How do you say this word? Like, where's the emphasis? Atomicity. That sounds right? Okay. Suspensions interrupt atomicity. Suspensions interrupt atomicity. For example, if an async function is running within a given context that is protected by a serial queue, async function is running within a serial queue. Reaching a suspension point means that the other queue can be interleaved on that same serial queue. Right. A classic but somewhat hackneyed example. Oh, this word, you don't see it that much. I think I know what it means, but lacking significance through having been overused. Wow. A classic but somewhat hackneyed example where this atomicity matters is modeling a bank. Indeed. I think this the book in the Gang of Four book. Was it in the Gang of Four book? The bank is like a hackneyed example. If a deposit is credited to one account, but the operation suspends before processing a matched withdrawal, it creates a window where those funds can be double spent. A more germane example for many Swift programming is a UI thread. The suspension points are the points where the UI can be shown to the user. So programs that build parts of their UI and then suspend risks preventing a flickering, partially constructed UI. Flickering, partially constructed UI. Right, so you draw part of the UI, and then you call async function, which suspends the thread. And then when the thread resumes, you draw some other thing. And then that means maybe the drawing can land into 2 different run loops. And yeah, run loops or display links, whatever. Requiring that all suspension points are marked allows programmers to safely assume that places without suspension points will behave atomically. So this is justifying why we require the await keyword, essentially, as well as to more easily recognize problematic non-atomic patterns. Because suspension points can only appear at point explicitly marked within an async function, long computations can still block threads. This might happen when calling a sync function that just does a lot of work, or when encountering a particular intense computation loop written directly in an async function. In either case, the thread cannot interleave code while these computations are running, which is usually the right choice for correctness, but can also become a scalability problem. Asynchronous functions that needs to do intense computation should generally run it in a separate context. When that's not feasible, there will be library facilities to artificially suspend and allow other operations to be interleaved. Async functions should avoid calling functions that are actually block the thread, especially if they can block it waiting for work that's not guaranteed to be currently running. For example, acquiring a mutex can only block until some currently running thread give up the mutex. This is sometimes acceptable, but must be used carefully to avoid introducing deadlocks or artificial scalability problems. In contrast, awaiting a condition variable can block until some arbitrary other work can get scheduled that signals the variable. This pattern goes strongly against the recommendation. Ongoing library work to provide abstractions and allow programs to avoid these pitfalls will be required. This paragraph is a little dense. Let me try to think about this. Avoid calling function that can actually. This first part is pretty intuitive. So acquiring mutex can only block until some currently running thread gives up the mutex. You lock a thread, and then you unlock the thread. It's easy to misuse it and introduce deadlocks. In contrast, waiting on a conditional variable can block until some arbitrary other work gets scheduled that signals the variable. Okay. This design currently provides no way to prevent the current context from interleaving code, while an asynchronous function is waiting for an operation in a different design. This omission is intentional, allowing for the prevention of interleaving. It's inherently prone to deadlock. Interesting. So this is saying the await, from a just semantic point of view, when you await for some functions, one possible design is you can choose to let the rest of the code execute as much as they can somehow. But that's not the case in this proposal because of the deadlock risk. Okay, async calls. Calls to an async function looks and act most like a call to a synchronous function or ordinary function. The apparent semantics of call to an async function are, I feel like we read this, as arguments are evaluated using the ordinary rules, including beginning access for any in-out parameters. We evaluate all the arguments, makes sense. The callee's executor is determined. This proposal does not describe the rules of determining the callee's executor. See the complementary proposal above about actors. Okay. Evaluate the arguments, evaluate the executor. Determine the executor, sorry. If the callee's executor is different from the caller's executor, a suspension occurs and the partial task to resume execution in the callee is enqueued on the callee's executor. Right, if we're going to a different context, we're going to suspend the current context. And then we create a partial task in the new context, queue it up so that, and which the partial task resumes the current context when it's time. The callee is executed with the given argument on its executor. During the return, if the callee's executor is different from the caller's executor, a suspension occurs during the return of the callee's executor. A suspension occurs and the partial task to resume execution in the caller is enqueued in the caller's executor. During the return, if a callee's executor is different from the caller's executor, okay, suspension occurs and the partial task to resume execution in the caller is enqueued. During the return, if the callee's executor is different from the caller's executor, okay, return, the suspension occurs and the partial task to resume execution in the caller is enqueued in the caller's executor. During the return, I don't know if that means the return of the callee when the callee is returning. Let's assume that's the reason. Does this make sense in that context? If the callee's executor is different, suspension occurs at the partial task to resume execution, including the caller. A suspension occurs. Another suspension. Finally, the caller resumes the executor. If the callee returned normally, the result of the calling expression is value returned by the function. Otherwise, the extension just throws an error that was thrown from the callee. This point, I understand mechanically what this is describing. I don't know why it needs to happen. Anyway, on the caller's perspective, async calls behave similar to synchronous calls, except that they may execute on a different executor, requiring the task to be briefly suspended. Note also that the duration of in-out access is potentially much longer due to the suspension of the call, so in-out references to shared mutable state that is not sufficiently isolated are more likely to produce a dynamic exclusion violation. That makes sense. Okay. Detailed design. And we're looking at code. Asynchronous functions. Function types can be marked explicitly as async. indicating that the function is asynchronous. So instead of taking a function as a callback, wait, what? Oh, you take a function that is async. Functional initializer. Oh my. Function or initializer declarations can also be declared explicitly as async. Initializer can be async as well. So you can await creating an object, right? Function initializer declaration. Okay. Raise hand. The type of what's the first one? Collect. Okay. The type of a reference to a function or initializer declares async is an async function type. If the reference is curried statically reference to an instant method, its inner function type is async, consistent with the actual rule for such references. Okay. Special functions like dinit and storage accessors cannot be async. Properties that can only have getter could potentially be async. However, properties that also have an async setter imply the ability to pass the property as an in-out. And drill down to the property of that property itself, which depends on the setter effectively being an instantaneous operation. Prohibiting async property is a simpler rule than only allowing get only async. So properties can't be async, even though in theory reading can be async. Wait, let's read that again. I think this can make sense. So when you're async setter, so set value and then a completion block. That's the way I think about this, right? Because in the imply the ability to pass the property as in-out and drill down into the properties, the property itself. So when you're dealing with a property of a property, you need it to be a normal, ordinary operation. Right. When you pass something by reference with an in-out and you mutate it, the mutation itself is a ordinary operation. It's not async. Therefore, setters cannot be async. Okay. If a function is both async and throws, then async keywords must precede throws in the type declaration. This same rule applies if async and rethrows. This order restriction is arbitrary but not harmful. Eliminates the potential for stylistic debates. Okay, that's fine. Asynchronous function types. Asynchronous function types are distinct from their synchronous counterparts. There's no implicit conversion from a value of synchronous function type to the corresponding asynchronous function type. However, the implicit conversion from a value from non-throwing asynchronous function to its corresponding throwing asynchronous function is permitted. That makes sense. So let's look at the example, right? Here's a sync non-throwing ordinary function, sync throwing ordinary function, async non-throwing, and async throwing. Okay. It's okay to convert from throwing form to throwing form. you can assign a non-throwing function to a throwing function, essentially. But you cannot assign a async function to a sync function, or vice versa, right? Yeah. One can manually create a sync closure that calls. You can make an async closure that calls synchronous function. So the lack of implicit conversion does not affect the expressiveness. Closures. Oh, there's syntax for closures, I guess. We do not propose implicit conversion from a synchronous function to an async function because it would complicate type checking, particularly in the presence of a synchronous and asynchronous overloads of the same function. Right, if you can convert, then you can overload. And that's complicated. All right, now let's talk about await. Await expressions. A call to a value of async function type, including a direct call to an async function, introduces a suspension point. Any suspension point must occur within an asynchronous context. Furthermore, it must occur within the operation of an await expression. Yeah. Await marks a suspension point. Yeah. Consider the following example. We ask the server to redirect the URL, and then we'll wait, and then the server figure out what the URL is asynchronously, return, and then at this point, this function that's executing is suspended until this new URL is available, and then we do the same thing, do something with the new URL. And this is a straight line code, straight line style. In this code above, in this code example, a task suspension may happen during the call to redirect and data task because they're async functions. Thus, both call expressions must be contained within some await expressions because each call contains a suspension point. Yeah, so this is, even though this statement is correct, it doesn't state the cause and effect. The correct way to think about this is, because a function may suspend, we have to mark it as await. Even though in practice it's probably okay to think await means a suspension point. The operand of an await expression must contain at least one suspension point. Makes sense? You can't call, if you call try without a throwing function to a throwing function, you get a warning, right? Although more than one suspension point is allowed within an await operand. For example, we can use one await to cover both suspension point from our example by rewriting it as, you just nested it in there. Okay. The await has no additional semantics like try. It merely marks that an asynchronous function is being made. The type of await expression is the type of its operand, and its result is the result of its operand. Yeah. It's just a marker. Yeah. It is important that async functions are clearly identifiable with the functions because they introduce suspension points. So this is more like, we need to mark it so the readers know there's a suspension point here, even though technically you don't have to if you are implementing a compiler, right? The compiler knows this function is will introduce a suspension point. The suspension point may be inherent to the call because of the async call must be in a different executor, or simply the part of the implementation of the callee. But in either case, it is semantically important and the programmer needs to acknowledge it. Await expressions are also an indicator of asynchronous code, which interact with inference enclosures. See the sections enclosure. Now I'm more and more interested in the closure. The suspension is killing me. A suspension point must not occur within an auto closure that's not part of the async function type. A suspension point must not occur within a deferred block. Defer executes when the closure, or when something goes out of scope, when the scope is finishing. And you can't suspend the function at that point because the context is finishing, so you cannot suspend it. It's already finished. Doesn't make sense. Doesn't compute. Okay. All right. Closure. Closures can be async function type. Such closures can be explicitly marked as async. Well, that's not surprising. So this is just like try, right? Throws. Yeah. An anonymous closure is inferred to have async function if it contains an await expression. Oh, so we get some inference here. Implicit. I don't know how I feel about this. This I can get on board. But if you have a signature, let me take some notes. I don't like this design. Let's use try as an example. So if f throws, and I make a closure that calls f, right? Well, let's use the other syntax. C equals throws. Well, first of all, I'm forced to call try. Try is a marker for the throwing function. Oh, so this is so it's consistent with the inference rules for try. Is consistent with inference rules for throws. That's pretty interesting. This I don't like this, but note that the inference of async on closure does not propagate its enclosing closures because these contexts are separably asynchronous or synchronous. For example, only closure 6 is inferred to be async in this situation. So there's a 5 and there's a 6. 6 calls a await for some function. So this is okay. Therefore 6 is async. But because 5 doesn't call an async function, it is not inferred as async. Yeah. It's interesting because 5 defines 6 and then kind of just throw it away. And there's also 7. 7 is inside of 6, but I think this one's more obvious. Just by looking at itself, it's not async. Overloading and overload resolutions. Existing Swift programs that include both synchronous and asynchronous entry points for an operation are likely to be designed to use 2 similarly named methods for each operation. Okay, do something completion handler. Do people do this? I hate it when people do this. It's like this interface is more general than this. So you can just make this optional or something if you really want to be succinct in your code. This call side with this method is being used called by the reference within the direct mapping of the second method into async. However, the signatures are now quite similar. Yes. If we were to replace async with throws, declaring the two methods above would produce a compiler error about an invalid recapitulation. Yep. Can't do that with tries. However, we propose to allow async function to overload non-async so the above code is well formed. This allows existing Swift program to evolve async version of the existing function without spurious renaming. Didn't you do this with the Python-like networking framework? I did, but these two things did do very different things. One is blocking, one is not blocking. I assume when they do this, this one is not blocking. Yeah, this is more like you have an underline. You can just imagine to implement this one version with completion handler. They just call this non-completion handler one, and then call completion handler with this return value. I could be wrong. Maybe this one also wraps it in a different thread or something. It's not something that I do a lot. Yeah, I don't know where this observation is from, but maybe it's not. Doesn't matter with what the design. Maybe the design has other better justifications than this. That the fact that this is a common use case. If we were to replace async with throws, declaring the two methods above would produce a compiler error about invalidated. Oh, okay, we already read that part. Given the call, overload resolution prefers a non-async function within a call because such context cannot contain a call to an async function. Oh, right. So because we can overload sync and async, now we have to resolve it based on the context of the call, right? So when you call do something now, which one is it? And the answer is we prefer a non-async function within a synchronous context. This is phrased in a funny way. Because such context cannot contain a call to an async function. I mean, that's just like duh. Like, if it's async context, synchronous context, you have to call the synchronous version. Furthermore, overload resolution prefers async function within an asynchronous context because such context should avoid synchronous blocking API. So this is the interesting point. Because in the asynchronous context, you could call the synchronous function. Now, we really need to answer which one is going to get called, and the answer is we're going to call the asynchronous version. When overload resolution selects an async function, that call is subject to the rules that it must occur within an await expression. Okay. Okay, I'm out of coffee. A function may not take an auto-closure parameter of an async function type unless the function itself is async. So you can make an auto-closure. Well, auto-closure has a signature, and of course in the closure signature, you can mark it as async. But if you take that an argument and yourself is not async, that won't compile. So consider this example. Here's a closure. It awaits for this thing. and then it calls this with its result, and then it prints hello. The await indicates there's a suspension point, because when we call this, we suspend, which is not actually the case. The suspension point is within the auto closure that is passed. Oh, if this thing takes auto closure. This causes problems. First, the fact that await appears to be prior to the call means closure could be inferred to have async function type, which also is incorrect. All the code in closure is synchronous. What? The fact that await appears to be prior to the call. Means that closure would be enclosed to have async. Oh, closure would be have async inside, which is also incorrect. All the code in closure is synchronous. Because the I kept thinking this is correct code, when in fact this is rejected code. Yeah, of course, this function as defined is synchronous. So this line is synchronous, this line is synchronous, therefore this line is synchronous. However, when you read await, you may think, oh, that means my closure that encloses it is inferred as asynchronous. Second, because an awaits operation only needs to contain a suspension point somewhere within it, equivalent writing would be this. But because the argument is auto closure, this rewriting is no longer semantically preserving. Okay. Anyways, our conclusion is you can't do this. Auto closure means yourself, taking an auto closure means yourself must be async. Okay, source compatibility is generally additive. Existing code does not use any of the new features and will not be impacted. However, if we choose two new contextual keywords, async and await, the position of the within the grammar allows us to treat async as a contextual keyword without breaking source compatibility. A user-defined async cannot occur within this grammatical position in well-formed code. The wait contextual keyword is more problematic because it occurs within the expression. For example, one could define a function await in function today. If you do this, you're screwed. Actually, I'm pretty sure I did this at some point. At work, no less. But I think that's no longer in there. Effect on ABI stability. They are additive to the ABI, so there's no effect because the existing functions are unchanged. ABI resilience is completely different from ABI from a synchronous function, so that does not affect it. Okay, nice. We're done with this. This is pretty straightforward. Super. It does have discussed a few nuances that I guess normally I wouldn't think of. But overall, it's a very simple proposal. Oh gosh, what was auto closure again? So auto closure is a thing where when you take an argument, right? Let's say you can take a closure like this. I don't know. It returns, let's say a closure that takes an int, right? So when you call this function, you pass in an int. Like something that returns an int, right? So this is normally how you would call it. But if you mark this as auto closure, right? So instead of calling this, you just give it an expression, and the compiler will wrap the expression. Well, this is a better way to show this. The compiler will wrap your expression so that it's equivalent to this. I'm sorry I didn't see your message earlier, but that's what autoclosure is. So the benefit of using an autoclosure is the same as having a closure, is just each time when you evaluate this function, right? The argument doesn't immediately get computed. Oh, let's make a better example. So there's a function that returns 42 every time, but maybe, right? Maybe. And then maybe you can think of this as like having some special property that maybe look at the time of the day and return either 42 or 43 or something like that, right? If you call a function that takes an int, if you call g, right, with return 42 maybe, what would happen is at this point, at the point of the call, this gets evaluated to become whatever integer is, and that integer is what g will take. But with autoclosure, with the same very similar looking, I don't know why I marked it as throws, that's interesting. With these two very similarly looking calls, this function won't immediately execute at this point, right? It will execute within the body of C. So when this happens, you have to do something like this to get the value. So this, if for some reason when you execute this this function, it may return different value under some conditions, the autoclosure version will get the fresh value sort of, and the G will get the stale value. Yeah, it's the little thing. Autoclosure. Okay. All right. We got another one out of the way. Almost 3 hours. I remember using this exactly once. Yeah. It's not definitely not something you think about every day. Let's do this next one. Let's do task API and structured concurrency. Structured concurrency. I'm also very excited to read all these Wikipedia articles. And those are going to be rabbit holes, and we won't do it on the stream. At least not on this stream. Where's the GitHub version of this? Oh, this one looks short. Why do they link different things? Oh, I probably clicked the discussion link. Pitch proposal. Okay. All right. Oh, this does not look short. All right. Let's go. Okay, this is also implemented. So we've already read about async await, but async await does not introduce concurrency per se. Yeah, that was the pitch. Yeah, looks long, but I'm going to try to not read out each single line of words, but kind of summarize what it says. So the async await proposal, yeah, like I said, it was just a syntax trigger, does not introduce concurrency. Ignoring the suspension points within an async function will execute in essentially the same manner as a synchronous function. Right. Now this link kept getting linked. I wonder if this gets updated. Let's see if Swift is mentioning here. Aha! The editors are swift in updating this. They moved swiftly. Enabling concurrent execution of asynchronous code with a model that's ergonomic, predictable, and admits efficiency problems. Admits efficient implementations. Okay. Let's make dinner. We chop vegetables, marinate meat, preheat oven, and then await. I can see where this is going already. Then we assemble the vegetable and meat into a ingredient, and then we take the assembled dish and throw it in the oven. Nice. So each step is asynchronous, and there are numerous suspension points. While waiting for the vegetable to be chopped, make dinner won't block the thread. It will suspend until the vegetables are available, then resume. Presumably, many dinner could be in various stages of preparation, with most suspended until the current step is completed. So that's an interesting thing. This sentence itself is pretty interesting. Yeah, so suspension just means we're waiting for a different thing to execute, but it does not mean blocking, right? Suspension and blocking is different. So the thread is free to do other things. And then when the async function finishes, right, it will queue up a new task for the thread. And the new task is to continue this function, right? So the thread model is not like fundamentally changing or anything. So even though the preparation is asynchronous, it's still sequential. It waits until the vegetable have been chopped before starting to marinate the meat, then wait again until the preheating the oven. That's obviously problematic, right? Huge patrons might be very hungry indeed. This is very playful write-up. To make dinner preparation go faster, we need to perform some of these steps concurrently. To do so, we can break down our recipes into different tasks that happen in parallel. These vegetables can be chopped at the same time that the meat is marinating and the oven is preheating. Sometimes there are dependencies between tasks. As soon as the vegetables and meat are ready, we can combine them into a dish, but we cannot put that dish into the oven until the oven is hot. All of these tasks are part of the larger task of making dinner. When all these tasks are complete, dinner is served. Yeah. So if I was asked, or I was asking how to write this in an interview, I would expect the answer to contain something like some queues and some tasks in the queues and dependencies between them and stuff like that, right? This proposal aims to provide the necessary tools to carve work up into smaller tasks that can run concurrently, to allow tasks to wait for each other to complete and to effectively manage the overall progress of a task. Okay. So the principles of structured concurrency All asynchronous functions run as part of a asynchronous task. Task can conveniently make child tasks that will perform work concurrently. Child tasks, okay? This creates a hierarchy of tasks, and information can conveniently flow up and down the hierarchy, making it convenient to manage the whole thing holistically. Okay, so let's see what that looks like. Oh, so there's a new keyword, async let. Child task with async let. Okay. Async let is similar to a let in that it defines a local constant that is initialized by the expression on the right-hand side of the equal sign. However, it differs in that initializer execution is evaluating a separate concurrent execution child task. On completion, the child task will initialize a variable in the async let and complete. Okay, so before we were calling await on the async function. Now instead of doing that, we can say async let that's a neat. I don't know what to think about it. It's just a completely new thing. Async let, okay? Async let. All right, this is something I didn't see coming. It differs in that initializer expressions is evaluating separate concurrently executing child tasks. On completion, the child task will initialize the async let and complete. Whoa. This seems OP. Because of the main body of the function executes concurrently with its child task, it's possible that make dinner will reach the point where it needs the value of async let. Say veggies. So we need veggies here, right? Before the value has been produced. To account for that, reading a variable defined by async let is treated as a suspension point. And therefore must be marked with await. Interesting. So the await marks a suspension point doesn't necessarily mean await must be preceding a function call. In this case, because we're reading a async let variable, that means this is a suspension point. Therefore, we must mark it with await. This is crazy. I mean, crazy good in a good sense. One can think of async let as introducing a hidden feature which is created at the point of declaration of the async let and whose value is retrieved at the wait. In this sense, async let is syntactic sugar for futures. Ooh. However, child tasks in the proposed structured concurrency model are intentionally more restricted than general purpose futures. Unlike a typical future implementation, a child task does not persist beyond the scope in which it is created. By the time the scope exceeds, the child task must either have completed or it will be partially cancelled. Implicitly cancelled. I don't know why I read partially. Implicitly. This structure both makes it easier to reason about the concurrent tasks that are executing within a given scope, and also unlocks numerous optimization opportunities for the compiler and the runtime. Bringing it back to our example, note that chop vegetables function may throw an error if, say, there's an incident within the kitchen knife. That thrown
Oh my god, there's some puns here. The thrown error completes the child task of chopping the vegetables. Um, the error then be the error will then be propagated out of the make dinner function as expected. On exiting the dinner, any child tasks that have not been completed will be automatically cancelled. Okay, so let's go through that example, right? So the first thing is we create async veggies, async let, async let, async let. So this will just keep executing without suspending the function, kind of like in JavaScript, right? And then we have await. So when this executes, if the veggies are not being chopped, then we'll be waiting on the veggies. Now, if chopped vegetable throws an error, that means we can potentially cancel these things if they're not done. Yeah. Okay. This is this level of syntactical power is I don't know. It's a little. I'm a little shocked, slightly shocked. I was thinking the await is itself is. I guess that makes sense because we just read the await proposal, and that's just a syntactical transformation almost. And it's not surprising that it doesn't grant like more powerful things. It just grant you shorter way to write the same thing almost. Not accounting for the extra creation of closures and copying of self and all that stuff. Those are actually performance gains. But this thing is just, these are things you have to do explicitly before creating dependencies between async tasks. Now you just have a built-in language syntax to do it. That's interesting. Okay, nurseries. The async await construct makes it easy to create a set number of child tasks. Sorry, the async let construct makes it easy to create a set number of child tasks and associate them with variables. However, the construct does not work as well with dynamic workloads where we don't know the number of child tasks we need to create because it is dependent on the size of data structure. For that, we need a more dynamic construct, a task nursery. A nursery defines a scope in which one can create new child tasks programmatically. As with all child tasks, the child tasks within the nursery must complete when the scope exits, or they will be implicitly cancelled. Nurseries also provides facilities for working with the child tasks by waiting until the next child task completes, for example. To stretch our example even further, let's consider chopped vegetables operation, which produce an array of vegetable values. With enough cooks, we could chop our vegetables even faster if we divide up the chopping for each kind of vegetables. So let's start a sequential version of vegetables. It's an async function. You take the raw vegetables and then you chop them in you iterate over each one of them, and chopped is also itself asynchronous. So you wait for each one to finish. This is distracting, but can array do this? I feel like array needs some enhancement in order to do this. Introducing async let into loop would not produce any meaningful concurrency because each async let would need to complete before the next iteration of loop would start. Let me think about this. So instead, if I say Oh, right. Because we need to assign the resulting chopped vegetables back into the array. Therefore, we need to reference it. Therefore, we're waiting for it to finish, right? And then we're suspended in the middle of the loop. So we have a new thing called with nursery. And this task thing, I guess, is part of the standard library. And you see with nursery, result type is a number and a vegetable. Okay, it's tuple with a number and vegetable. Okay, so you take the indices of the vegetable. You make nursery.add. Okay, so nursery is kind of like a container almost. And then here at the end, you call nursery.next. And I assume next will happen and whenever whenever a nursery.add gets called, right? And then when that happens, you just assign it here, and you do this in a loop. And when nursery.next is nil, we're done. Wait, how does this terminate? This function introduces a new scope in which child task can be created using the add method. The next method waits for the next task to complete, providing the result value from the child task. In our example, each child task carries the index where the results should go, along with the chopped vegetables. As with the child task created by async let, if the closure passed with its nursery exits without having completed all child tasks, the remaining child tasks will be automatically cancelled. Okay, so adding is like completes, I guess, pretty quickly. And add completes even though asynchronously, but should be pretty quickly, right? And the nursery will dispatch this task in different queues. Okay, so after they're dispatched, they're done. And then when this task finishes, it will emit in next. You can get the result from next, which also returns them asynchronously. So you just await that. Okay. Okay. Detached task. Thus far, every task we have created has a child task. It's a child task, whose lifetime is limited by the scope in which it is created. This does not allow for new task to be created that outlives the current scope. The run detached operation creates a new task. It accepts the closure, which will be executed as a task as the body of the task. New detached task to make dinner. Await make dinner. Make detached is a handle. Yes. Which can be used to retrieve the result of the mission. You just call get or cancel if it's no longer unlike child tasks. This is more like the dispatch queue stuff. unlike child tasks, detached tasks aren't cancelled even if there's no remaining user of the task handle. So run detached is a suitable way of operation for which program does not need to observe the completion. Okay. So run detached is kind of like a fire and forget. You could use it as fire and forget, even though if you don't want to forget it, just keep around the handle. Okay, detailed design. Structured concurrency. Any concurrency system must offer certain basic tools. There must be some ways to create a new thread that will run concurrently with existing threads. There must also be some ways to make a thread wait until another thread signals to continue. These are powerful tools, and you can write very sophisticated system within them. But they are also very primitive tools. They make very few assumptions, but in return they give you very little support. Imagine there's a function which does a large amount of work on the CPU. We want to optimize it by splitting the work across 2 cores. So now the function creates a new thread, does half of the work in each thread, and then has its own original thread wait for the new thread to finish. On a more modern system, the function may add tasks to a global thread pool, but the basic concept is the same. There's also a relationship between the work done by these 2 threads, but the system doesn't know about it. That makes it much harder to solve the systematic problems. For example, suppose a high priority operation needs a function to hurry up and finish. The operation might know to escalate the priority of the first thread, but really it ought to escalate both. At best, it won't escalate the second thread until the first thread starts waiting for it. It is relatively easy to solve this problem narrowly, maybe by letting the function register a second thread that should be escalated. But it will be an ad hoc solution that might need to be repeated in every function that wants to use concurrency. Yes, so I want to split my work into 2 other threads, and then I need to give them the correct priority. And then if I do that again somewhere else, I need to re-implement that. Structured concurrency solves this by asking programmers to organize their use of concurrency into high-level tasks and their child component tasks. These tasks become the primary unit of concurrency rather than low-level concepts like threads. Okay. Structuring concurrency this way allows information to naturally flow up and down the hierarchy of tasks, which would otherwise require carefully written support at a high-level abstraction and every thread transition. Yeah, basically not messing with the thread. That's a benefit of using queue as well. This in turn permits many different high-level problems to be addressed with relative ease. We're already seeing an example of that, dependencies, right? Okay, for example, it's common to want to limit the total time spent on a task. Some APIs supports this by allowing a timeout to be passed in, right? But it takes a lot of work to propagate timeouts done correctly through every level of abstraction. This is especially true because end programmers typically want to write timeouts as relative durations, but correctly computing representation for libraries to pass around internally is an absolute deadline. Now plus 20, yeah. Under structured concurrency, a deadline can be installed on a task and naturally propagate through arbitrary level of APIs, including child tasks. Similarly, it's common to want to be able to cancel an active task. Asynchronous interface that supports this often do so by synchronously return a token object that provides some sort of cancel method. This significantly complicates the design of APIs, so often isn't provided. Moreover, propagating tokens or composing them to cancel all of the active work can create significant engineering challenges for a program. Yeah, you pass things around. Is extra code, yeah. Under structured concurrency, cancellation naturally Pyro. This seems like a typo, right? Propagate. Yeah. Propagates through APIs and down to child tasks, and APIs can simply install handlers to respond to cancellation. Right. You cancel the parent because the child parent has a relationship with children. They all get cancelled. GUI often rely on task prioritization to ensure timely refresh and represents responses to events. Under structured concurrency, child tasks naturally inherit the priority of the parent tasks. Furthermore, when higher priority tasks wait for low priority tasks to complete, the low priority task and all of its children tasks can be escalating priority, and this will reliably persist even if the task is briefly suspended. Interesting. Many systems want to maintain their own contextual information for an operation without having to pass it through every level of abstraction, such as a server that records information for connections currently being serviced. Structured concurrency allows this to naturally propagate down through async operations as sort of task local storage, which can be picked up by child tasks. Systems that rely on queues are often susceptible to queue flooding, where the queue accepts more work than it can actually handle. This is typically solved by introducing back pressure. Queue stops accepting new tasks, and the system that are trying to in-queue work there respond by themselves stopping accepting new work. Actor systems often subvert this because it is difficult at the scheduler level to refuse to add work to an actor's queue, since doing so can permanently destabilize the system by leaking resources or otherwise preventing operations from completing. Structured concurrency can offers a limited cooperative solution by allowing system to communicate up to task hierarchy that are coming under distress. Limited cooperative solutions to communicate up this task hierarchy that they are under pressure, potentially allowing parent tasks to stop or slow the creation of presumably similar new work. Okay, this kind of communication I haven't seen an example of, so it's kind of hard to conceptualize. The proposal doesn't propose solutions for all of these, but early investigations show promise. Okay, so what is a task? It is a basic unit of concurrency in the system. It is an analog of a thread for asynchronous function. I think this means synchronous functions. There's some typos here. Can we submit pull requests? I guess people are already catching them. Fix typo. Fix typo. Small typo. Wait, why didn't they find the typo I was looking at? Wait, this is from 2018. Huh. Okay. What about my typo? I found a bunch of typos. Well, some of them are just typos, misspellings. But this sentence appears to be, let's see. A task is the analog of a thread. But I think this is an analog for thread for synchronous functions, not asynchronous, right? A task, you put a task into this concurrency system, right? Just like you put a synchronous function to execute on a thread. Right, so this is a more serious typo. All asynchronous functions run as part of the task. A task run one function at a time. Single task has no concurrency. When a function make an async call, the call is a. Similarly, when a function returns from an async call, the caller resumes running on the same task. Oh, this is bothering me. I'm gonna. Do I have a Swift evolution repo? I don't. Slightly surprising. Okay. Let's clone this repo. Actually, clone this repo. Where is it? Oh, excuse me. And then let's add a remote. Doug Gregor. Trade structured concurrency. Oh. Structured concurrency. I assume that's the branch name. There we go. Then structured concurrency. Okay, finally. Where is it? Tasks. Some sort of header. Okay. Synchronous. Yes. Typo. Teehee. Wait. Okay, so now I need to fork this. I'm surprised I didn't have a fork. Fork. I do have a fork. What? Oh, but it's not. Remote set URL. Swift evolution. Okay. No, that's not what I meant. Ah. Head repo is mine. Base repo is Doug Gregor. Okay. This branch is concurrent. Structure concurrency. T. There we go. Oh, I shouldn't have closed it, huh? Oh. Okay, let's go back to. Oh, finally. Okay. All right. So, as we were saying, a task is analog to a function in the synchronous world. And synchronous functions do not necessarily run as a part of a task. Swift assumes the existence of an underlying thread system. Tasks are scheduled by the system to run on these system threads. Okay. Tasks do not require special scheduling support for the underlying thread system. Although a good scheduler would take advantage of some of the interesting properties of Swift's task scheduling. Sorry, give me 1 second. All right. So there are some interesting properties of Swift's task scheduling. Task can be suspended. It's not currently when it is, it's not currently running. It may be schedulable, meaning that it's ready to run and it's just waiting for the system to instruct a thread to begin executing it, or it may be waiting on some external event before it can become schedulable. So it can be suspended, schedulable, waiting. Let me just think about this real quick. This analog of a thread. Oh, actually, I think that sentence actually makes sense. Let me close that. So it's saying, hold on. So it's saying, I don't know. I don't know. Task is a basic unit of concurrency. It is the analog of a thread. So it's comparing a task to a thread. No, it is. It does make sense. Gosh darn it. Let's just open this in a new window and go back to here and try to make that pull request again, maybe. All right. Sorry about that. A running task is currently running a thread. It will run until it either returns its initial function and become completed, or reach its suspension point and become suspended. At a suspension point, it may become immediately schedulable. If, say, its execution just needs to change actors. That makes sense. Completed task has no more work to do and will never enter any other state. So suspended can be schedulable or waiting. Running task can become completed or suspended. Completed task is the eventual final state. The way we talk about execution for tasks and asynchronous functions is more complicated than it is for synchronous functions. An asynchronous function is running as part of a task. If task is running, it and its current functions are also running on a thread. Right, so tasks can run multiple asynchronous functions, and tasks themselves and all those functions are implemented on a thread with the thread. Note that when an asynchronous function calls another asynchronous function, async function, we say that the calling function is suspended, but it doesn't mean the entire task is suspended. From the perspective of the function, it is suspended, waiting for the call to return. From the perspective of the task, it may have continued running in the callee. Right. So it's entirely possible that asynchronous function runs on the same thread, therefore the same task on the same thread. Or it may have been suspended in order to, say, change the different execution context. Right, we're running something on a different thread. Tasks serve 3 high-level purposes. They can carry scheduling information such as task priority. They serve as a handle through which the operation can be canceled, queued, or manipulated. They can carry user-provided task local data. Okay. They can carry priorities. They can serve as a handle. They can carry local data. At a lower level, the task allows the implementation to optimize the allocation of local memory, such as for asynchronous function context. It also allows dynamic tools, crash reporters, and debuggers to discover how a function is being used. Child tasks, a asynchronous function. Wow. An asynchronous function can create a child task. Child task inherits some of the structure of the parent task, including its priority, but can run concurrently with it. However, this concurrency is bounded. A function that creates a child task must wait for it to end before returning. This structure means that the function can locally reason about all work currently being done for the current task, anticipate the effect of canceling the current task, and so on. It also makes spawning the child task substantially more efficient. Right, so this is a structure where the function is aware of all the child tasks, so they can handle them, they can anticipate any of them, and do things. Of course, a function's task may itself be a child of another task, and its function may have another children. Its parent may have other children. A function cannot reason locally about these. Yeah, you cannot reason about your ancestor tasks. But the feature of this design can apply to an entire task tree, such as cancellation, only apply downwards and don't automatically propagate upwards in the task hierarchy. And so the child tree still can be statically reasoned about. Yes, because you only have a local view, right? So you can reason about it. So if child tasks did not have bounded duration and so could arbitrarily outlast their parents, the behavior of a task under these features would not be easily comprehensible. So that makes sense. So basically, we're leveraging the lexical scope of a function to use as the scope of to use as a task hierarchy, the scope for task hierarchy. I think earlier I took a note about scope-based mechanism for waiting values for multiple tasks. So that answers this question. That's what the scope-based mean. Nice. Okay. Partial tasks. The execution of a task can be seen as a succession of periods where the task was running. Okay. Succession of periods where the task was running. So, okay, task runs and then for a period, and then it runs for another period, each of which ends at a cessation point, or finally completion of the task. Okay, so it can suspend and resume and then eventually complete. These periods are called partial tasks. Partial tasks are a basic unit of schedulable work in the system. They are also the primitive through which asynchronous functions interact with the underlying synchronous world. For the most part, Programmers should not have to work with directly with partial tasks unless they are implementing a custom executor. Right, when you are working with a custom executor, you are responsible for connecting the operating system or whatever the entity that executes your code. Could be a TPU or whatever. Then, of course, when something is supposed to be suspended, you need to actually do something and resume and all that. Executor is a service which accepts the submission of partial tasks and arrange for some threads to run them. Threads, sure. What is a thread, really? The system assumes that executors are reliable and will never fail to run a partial task. The asynchronous function that is currently running always knows the executor that is running on. This allows the function to avoid unnecessarily suspending when making a call to the same executor. Okay. And it allows the function to resume executing on the same executor it started on. An executor is called exclusive if the partial task submitted to it will never be run concurrently. Specifically, the partial task must be totally ordered by the happen before relationship. Given any two tasks that were submitted and run, the end of one must happen before the beginning of the other. Okay. Executors are not required to run partial tasks in the order they were submitted. In fact, they should generally honor task priorities over submission order. Okay. Swift provided default executor implementation, but both actor classes and global actors can suppress this and provide their own implementation. So that means on each platform, the language now, the compiler now directly deals with threads for you implicitly with this. Assuming, thread is the most convenient way to implement a executor. Generally, end user need not to interact with the executor directly, but rather use it as well. Okay. Task priorities. You have a priority method, may inform decisions the executor take about and yep, it's just a property, some information, right? Executor may utilize priority information to attempt to run higher priority first and then continue to lower priorities. It may also use priority information to affect the platform thread priority. The exact semantics of course, is up to the implementation of the executor. Child task automatically inherits the parent task priority. Nice. It's kind of like threads, right? Detached tasks do not inherit priority because they semantically do not have a parent task. Of course. The priority level for a task is set by passing it to run detached priority when starting a top level task. The child task of task will inherit this priority. So you can only set it once when it's a detached task. The priority of a task does not necessarily match the priority of the executor. Okay. For example, the UI thread on Apple platform is a high priority executor. Tasks submitted to it will be run in high priority for the execution of its time on the thread. This helps to ensure the UI thread will be available to run higher priority task if it is submitted later. This does not affect the formal priority of the task. Okay. Escalation. So sometimes you need to escalate. If a task is running on behalf of an actor, higher task is queued on the actor. Task may temporarily run the priority of the higher queue task. Doesn't affect the child tasks or the actual priority. Right. So if you queue a task that's higher than your own task is on behalf of an actor. So presumably the actor itself has a fixed priority, but it got queued for a high priority task than its original one. So it doesn't change this original priority, but the task itself may run with a higher priority. Task agreed to task handle, and higher priority task calls await, try, handle, get. Then the priority will change. Okay. Cancellation can be cancelled asynchronously by any context that has reference to the task or one of its parent tasks. Cancellation can be triggered explicitly by calling cancel. Can also trigger automatically, for example, when a parent task throws an error out of scope with unweighted children task. Okay. Such an async lag. Yep. The effect of cancellation within the task is fully cooperative and synchronous. Cancellation has no effect at all unless something checks for cancellation. Conveniently, most tasks that checks for cancellation reported by cancellation error. Accordingly, there must be throwing functions, and calls to them must be decorated with some form of try. As a result, cancellation reaches no additional control flow paths with asynchronous functions. Right. So if something got cancelled, you get a cancellation error. You can always look at the function and see places where cancellation can occur. As with other thrown errors, defer block can be used to clean up effectively after cancellation. With that said, the general expectation is that asynchronous functions should attempt to respond to cancellation by promptly throwing or returning. In most functions, it should be sufficient to rely on lower level functions that can wait for a long time. For example, task handle get, to check cancellations and abort early. Functions which perform a large amount of synchronous computations may wish to periodically check for cancellation explicitly. Okay. Cancellation has two effects which triggers immediately with the cancellation. Flag is set in the task, which marks it as having been cancelled. Okay. So you have a task handle, you can check it. Once this task is flagged, it's never cleared. Operation running synchronously as part of the task can check this flag and conveniently expect it to throw in a cancellation error. You check it and you can throw a cancellation error. Any cancellation handlers which have been registered on the task are immediately run. This permits a function which needs to be responded to do so. We can introduce cancellation with a version of chop vegetables. Okay, so unfortunate accident with knife error. When we chop the carrot. On line 1, we start a new child, and I suppose this calls the chopping function throws an error because of this asynchronous error is not immediately observed by chopped vegetables. Right. And we proceed to start a second task. Yeah, because it's asynchronous, right? So at the beginning of the execution of chopped carrot, we don't necessarily throw. So it may throw later. So we just move on to the next line and execute this. Okay. But when we eventually will wait for the result of the chopped vegetables, right? So line 3, wait for the chopping task, causes us to throw an error that's thrown from chop. Okay. So when you await for the actual result, the task to finish, we can catch the error here, which also means we have to use try because this is potentially throwing the cancellation error. Okay. The cancellation of task is synchronous and cooperative. Function which do a lot of synchronous computation may wish to check explicitly for cancellation. They do so by inspecting the task's cancelled status. So you can check cancellation. Okay. If it's cancelled, we throw the cancellation error ourselves. Okay. Okay. No information is passed to the task about why it's cancelled. Task may be cancelled for many reasons, and additional reasons may accrue after the initial cancellation. For example, if the task failed to immediately exit, it may pass a deadline. The goal of cancellation is to allow tasks to be cancelled in a lightweight way, not to be a secondary method for inter-task communication. So common use case for cancellation is cancel task because they are taking too long. This proposal introduced the concept of deadlines and introduced them to cause a task to consider itself as cancelled if deadline is executed. We intentionally use deadlines, points in time, as opposed to timeouts, duration of time. This is because deadlines compose correctly. Working with timeouts is prone to errors where the deadline is accidentally extended because of a full timeout is reused. Yes, you can say 20 seconds, but somehow you pass the 20 seconds somewhere else, and that somewhere else has a different starting point than it's not really 20 seconds anymore. For convenience, we allow code to use a relative timeout when setting the deadline up. Okay, when you set it up, this will be immediately translated into absolute deadline. So dinner preparation with deadlines. So here we're making a task with deadline 2 hours. And then inside of it, we have a deadline of 20 minutes to marinate meat. We take, and then when we wait for everything to cook, we are passing in a duration. Oh, what is duration? Ooh. This is a new thing, right? Okay. In the example above, we set 2 deadlines. The first deadline is for 2 hours from the start and apply to the entire dinner preparation task. Second deadline is 30 minutes and it applies only to the portion of the task. Note that we await the chopped vegetable before beginning the marinade. Is this how you spell marinade? The verb, the noun? I never knew that. Okay. This is to illustrate the following point. Imagine somehow the chopping up vegetable for some reason cook 1 hour and 40 minutes. Now that we get to the meat marination step, we only have 20 minutes left in our outer deadline, yet we attempt to set a deadline in 30 minutes from now. If we had just set a timeout for 30 minutes there, we would well past the other deadline. Instead, we task automatically notice that the new deadline is actually greater and thus is ignored. The task will be cancelled appropriately at the 2 hour mark. Okay. You can also interact with deadlines programmatically. Cook function knows exactly how much time it will take to complete. Just check for cancellation at the beginning of the cook function only meant that the deadline hasn't been cancelled yet. Aha. Like this. Current deadline. So task, yeah, you get the current deadline of the task. You look at the remaining duration. And if it's not enough time, you can just throw an error. Thanks to this, functions which have a known execution time can proactively cancel themselves before even starting the work, which we know would miss the deadline in the end anyways. Nice. Child tasks with async let. Asynchronous calls do not themselves introduce concurrent execution. However, async functions may conveniently require work to be run in a child task, permitting it to run concurrently with an async let. Right. So if you mark it as async let, that means the next line, whatever it is, will execute after this is scheduled, and as opposed to when this is executed when this is finished. Any reference to variable that was declared async let is a suspension point, equivalent to call to an async function, so it must occur within a await. So when you later refer to this result, you must use await. The initializer of the async let is considered to enclose by implicit await expression. Implicit. So there is an implicit await expression here. If the async let can throw an error, then each reference to variable declared within async let is considered to throw an error, and therefore must also be enclosed by one of the tries. One of the variable for given async let must be awaited at least once along all the execution paths before it goes out of scope. So here we're awaiting this. So there's some. Okay, because this is async let, so we must await it somewhere in the branch. Otherwise, yeah, okay, that makes sense. This is really smart. If the scope of an async let exists with a throw error, the child task responding to the async let is implicitly cancelled. If the child task has been completed, its result is discarded. Child task with nurseries. In addition to async let, this proposal also introduced an explicit nursery type, which allows for fine-grained scoping of tasks with such nursery. Okay, we've seen this earlier. This is just more details, right? Task may add it dynamically to a nursery, meaning one may add a task for each element of a dynamically sized collection to a nursery and then have them all be bound to a nursery lifecycle. This is in contrast to async let declarations, which only allow a statically known compile time number of tasks. Yes, because async let is declaring a variable and associate a task with that variable. Therefore, each variable must be defined. Therefore, it's static. With nursery, you get this block, right? And in the block, you get to declare which task, the return type of each task, and then you take a block to execute the task, which defines the task itself. Okay, interestingly, the block has a mutable task result thingy. Okay, nursery can be launched from any asynchronous context, eventually returning a single value, body result. Task may be added to it dynamically, as we saw in chop vegetables. Yes, we saw nursery.add, and then each time we add in the index and a asynchronous call that chops the vegetables at that index. Okay, and that was inside of a for loop. And the nursery enforces awaiting for all tasks before it returns, asserting that it is empty when returning the final result. Okay, so here are the APIs. It has some ownership annotations. So we can add task with handle. Next, this is how we get the returning value from the nursery. So after you add all these asynchronous things into the nursery, with a dynamic manner, the next thing is you call nursery.next, right? And then each time you call it, it will give you a result until it doesn't. Yeah, because the nursery knows how many tasks it's being added, so when it returned that number of results, it will start returning nil, and that's when you can finish waiting for the results. And in our chop vegetable example, because the return type is an index and the chopped vegetables, you can kind of put that back to a collection according to the index. So that's how you parallelize, like working with a collection. Okay. Nursery guarantees that it will wait for all tasks that were added before it returns. So the waiting can be performed either by the code within the nursery itself or transparently nursery itself when returning from it. Okay. Chop vegetable example, we not only added vegetable chopping tasks to the nursery, but collect the result, chopped up results. Oh, this is actually what I just said, but here it is. You have an array of vegetables, raw vegetables. You want to chop them asynchronously. So the way you do it is you add each vegetable to the nursery, and then later you say nursery next, and then give me the result. Each time it gives you one chopped vegetables, and that's how you get it back. So this will just kick off these asynchronous tasks and move on. Yep, and then you get this, and then this will wait for the results. So now we're talking about throwing and cancellation. Pointing out is adding a task could fail because the nursery could have been cancelled when we're adding the task. So the task in nursery by default handles room errors using like musketeers would say there's one for all and all for one. In other words, yeah, if a single task throws error, all the other tasks, if you when you chop carrots, there's an incident, then you throw out all the other chopping tasks. Chopping onions make you cry. Onion will throw an error into the nursery, causing all the tasks to be cancelled automatically. So when it throws, so when the task can throw, you must mark it with try, and that kind of connects back to the classic throw and catch system. Okay. Parent task cancellation. Nursery can be cancelled if the task in which it was created is cancelled. Cancellation nursery cancels all the tasks within it. Attempting to add more tasks into a cancel nursery without a cancellation error. Okay. Work item. It's an async function that check cancellation. Okay. So here we're creating a top level task with a handle. And then in the task, we use the nursery. For each nursery, we have a processed variable. And then we take our list of work items and add them to the nursery, wait for them. Each time it's done, we add a process and return the processed number. And then, we cancel it. We cancel the entire task. Give me 1 sec. All right. Yeah, so there are many ways tasks can be canceled, but this time we just cancel them directly. So the task is the parent of nursery, then as such the cancellation will be propagated. Nursery will automatically check for the cancellation of the parent task when creating a new child task or waiting for a child task to complete. Adding a new task may also suspend if the system under substantial load as a form of back pressure on the queue of new tasks being added to the system. That's why adding a task itself is a asynchronous thing. Yeah. This consideration allows the program to write straightforward, natural feeling code that will still do the right thing by default. Implicitly awaited task. So I think a lot of this is like from a programmer point of view, things are simplified and very structured, but the complexity lands in the implementation of an executor. Sometimes it's not necessary to gather the result of asynchronous functions because maybe void returning unidirectional. In this sense, we can rely on the nursery implicitly await for all the tasks started before returning. In the following example, we need to confirm each order that we received. However, that confirmation does not return any useful value to us. Either it is void or we simply choose to ignore the return value. So with nursery, we just add the task and that's it. Confirm order function will only return once all confirmation is completed because nursery will at the end edge of its scope await any outstanding. Okay. Detached tasks. Detached tasks are the two except patch API offered by this proposal. The other one being unsafe continuation API discussed in the next section. For when structured concurrency rules are too rigid for specific instances. Okay. Running at the previous mentioned example of making dinner in a detached task, but following the missing types and details. So here is the task, run detached, so we make dinner. And then dinner just, okay. Dinner.get, dinner handle.get. Okay, now we get a handle to the task, and then someone can cancel it, and you can get the result from the task. The task handle returns from the run detached function serve as a reference to an in-flight task, allowing them to be awaiting or canceling the task. The get function is always throwing. Also, the cancellation error. So awaiting a get is always throwing, even if the wrapped operation was not throwing itself. So this is tasks interface. This is handles interface. You can get asynchronously throwing, or you can cancel. Okay. Typo. The low-level execution of async code occasionally require escaping the high-level abstraction of an async function and nurseries. Also, it is important to enable APIs to interact with existing non-async code, yet to be present to the user of such API a pleasant use function-based interface. For such situations, unsafe throwing continuation. With unsafe throwing on continuation, unsafe continuations allows for wrapping existing complex callback-based APIs and presenting them to the caller as if it's a playing asynchronous function. Rules for dealing with unsafe continuations. The resume function must only be called exactly once. I'm going to fix this typos. Code Swift evolution. Playing async. APIs. Par. There's a word propagation that's misspelled. Was it misspelled as para? Yeah. Propagates. challenge. Wait. Pro. Wait, how do you spell proactively? Programmatically. Wait, is this not a programmatically? Okay. Further. Unawaited, that's fine. Schedulable. Because programmatically, sometimes it's spelled correctly. Just plain spelling errors. Oh, I deleted a bunch of trailing closures. Trailing white spaces. Sorry, let's just take a break and fix some typos, yeah? Okay, here we go again. We're going to target dogs. Ah, come on. I'm gonna fix this here first. Oh no. Oh no, no, no. I pushed it to origin. Ah! The hazard of having push access. Okay. Now. Wait, what? Oh, master, no. Okay. I think we're almost done with this one, right? Yeah. So this last piece. So this is where you can hook in your callbacks with the async await system, with the task. So here we're making the unsafe throwing continuation. We get this continuation object in this closure, right? And then we go and get those vegetables. And then we call resume. Okay. So here's our callback based function, and then we can wrap it into an async function. Right. The reason it's unsafe is because you need to carefully place the resume calls, and it needs to be called only once. And this is purely additive to from an ABS perspective. Okay, we've done another one. Let's keep going. How many do we have left? Swift authentication. Not this one. Hold on. I think this might be it, but let's click on this. All right. Okay. Actor and actor isolation. Proposal. Okay. I'll be right back. Take a break. Hi, Gilad. Welcome back. Yeah. I think the Objective-C one, I'm hoping it's going to be simple. I mean, at least it's the least interesting. It just probably says some rules for importing Objective-C APIs. And for us pure Swift folks, that's like, okay, good to have, but doesn't affect me. All right. Actors. So actor model involves entities called actors. Actors can perform local computation based on his own state, send messages to other actors, and act on messages received from other actors. They run independently and cannot access state of other actors, making it a powerful abstraction for managing concurrency in language applications. The actor model has been implemented in a number of programming languages such as Erlang and Pony, as well as various libraries like Akka and Orleans. The This proposal introduced design for actors in Swift, proving a model for building concurrent programs that are simple to reason about and safer to from databases. One of the more difficult problems in developing concurrency programs is dealing with data races. Data races occurs when the same data in memory is accessed by two concurrently executing threads, at least one of which is writing to the memory. So it has to happen both, right? Two are accessing, one is writing. At least when this happens, the program may behave erratically, including spurious crashes of program errors due to corrupted internal state. Okay, data races are notoriously hard to reproduce and debug because they often depend on two threads getting scheduled in a particular way. Thread sanitizers helps, but they are reactive as opposed to proactive. They help find existing bugs, but cannot help preventing them. Okay, actors provide a model for building concurrent programs that are free of data races. They do so through data isolation. Each actor protects its own instant data, ensuring that only a single thread will access that data at a given time. Actors shift a way of thinking about concurrency from raw threading to actors, put focus on actors owning their local state. This proposal provides a basic isolation model that protects the value type state of an actor from data races. A full actor isolation model which protects other states, such as reference types, is left as future work. Great. So, proposed solution. We have actor classes. We saw that in the roadmap. Actor class is a form of class that protects access to its mutable states, therefore introduced with actor class. Actor class behaves like a class in most aspects. They can inherit, they have methods, properties, and subscripts. They can be extended and conform to protocols, be general, and be used with the generics. The primary difference is that actor class protects their state from data races. This is enforced statically by the Swift compiler through a set of limitations on the way in which actors and their members can be used, collectively called actor isolation. Actor isolation is how actors protect their mutable state. For actor classes, the primary mechanism for this protection is only allowing their stored instant property to be accessed directly on self. For example, here's an method that prevents attempts to transfer money from one account to another. Okay, we have a bank account. This is an extension to it. We have a transfer method that takes another background and some amount. And then if there's not enough balance, we just throw an error. And otherwise, we'll print out the amount, the owner name, and the other account's owner name. Then we mutate the balance, and then we attempt mutate the other account's balance. And this is a compiler error. If bank account were normal classes, the transfer amount to method would be well formed, but would be subject to data races in concurrent code without external locking mechanism. With actor class, the attempt to reference other.balance triggers a compiler error because balance may only be referenced on self. As noted in the error message, balance is actor isolated, meaning that it can only be accessed from within the specific actor, or it is tied. Only be accessed from within the specific actor it is tied to or isolated by. In this case, it is an instance of bank account referenced by self. Stored properties, computed properties, subscripts, and synchronous instances methods like transfer amount to in actor classes are all actor isolated by default. On the other hand, the reference to other.owner_name is allowed because owner name is immutable, defined by let. Once initialized, it is never written, so there can be no data races in accessing it. Owner name is called an actor independent because it can be freely used from any other actor. Constants introduced with let are actor independent by default. There's also an attribute actor independent. Actor independent declarations. Sounds like some anti-union stuff. Let's open this in a new window. What is it called? Actors Union or something? Screen Actors Guild. Wait until Screen Actors Guild hear about the proposed, what is it called? Actor independent declarations in Swift. There you go. Live shade posting. All right. Okay, so all the methods, subscripts, by default, everything in actor class that traditionally belongs to a class, member of a class, they're considered actor isolated, right? They will follow these isolation rules. Constant defined by let are only truly mutable. I feel like I've read this in the roadmap before. Right. So even if your property is let, it is only immutable if it's a value type or a immutable reference type. If it's a reference type, then it's just a pointer. Then it can be muted, whatever. Yep. Compile time actor isolation checking, as shown above, ensures that code outside of the actor does not interfere with the actor's mutable state. Great. Asynchronous function invocations are tuned. Asynchronous function invocations are turned in queues of partial tasks. Asynchronous function invocations are turned in queues of partial tasks, wrapping those invocations to the actor's queue. Okay? So actor has a queue. This queue, along with an exclusive task executor bound to the actor. So an actor has a queue, has an executor, functions as a synchronization boundary between the actor and any of his external callers. Right, so if I call a method on an actor class, let's say, then all the calls are synchronized by the queue and the executor. For example, if we were to make a deposit to a given bank account, we could make a call to a method deposit amount, and that call would be placed on the queue. The executor would pull tasks from the queue. That's what the queue is for. Okay, so the executor has a queue, and the queue queues up tasks, and the executor takes tasks from the queue, ensuring the actor never is concurrently running on multiple threads because it has an exclusive executor, and will eventually process the deposit. Synchronous functions in Swift are not amenable to being placed on a queue to be executed later. Therefore, synchronous instance methods of actor classes are actor isolated and therefore not available from outside the actor class. So if you have a normal method, because it cannot be enqueued and executed by the executor, therefore you can only access it yourself. Others cannot access it. So I guess if you want to expose it, you have to wrap it or something, or just define it as async. So example here, deposit synchronously, we check, we manipulate, and then if you want to use it here, take a list of bank account, deposit amount synchronously, tough luck. should be noted that isolation has a new dimension separate from access control. That's correct. To the decision-making process, whether or not one is allowed to invoke a specific function or an actor. Specifically, synchronous functions may only be invoked by the specific actor instance itself, and may not even by any other instance of the same actor class. Right. Not even by the same actor class of other instances. And all interaction with an actor must be performed asynchronously. Semantically, one may think about this as the actor's model of messaging to and from the actor. Asynchronous functions provide a mechanism that is suitable for describing such operations and are explained in depth in the complementary async await proposal, which we read earlier. We can make the deposit amount instance async and thereby make it accessible to other actors. Right. Just make it async for head. Now the call to this method is well formed. We just need to await it. Semantically, the call to deposit is placed on the queue for the actor account. This is like reiterating the information so that it will execute on the actor. If that actor is busy executing a task, then the caller will be suspended until the actor is available so that other work can continue. See the section on asynchronous call in the async await proposal. Again, read it. Right. So we can properly implement the transfer found from one account to another. So we make this async, and then when we are depositing to the other account, we just await it because it's asynchronous. It's accessible, it's not isolated, and we must await. Okay. So closures and local functions. The restriction only allowing access to actor isolated declaration on self only works so long as we can ensure that the code in which self is valid is executing non-concurrently on the actor. For methods on the actor class, this is established by the rules described above. Async functions calls are serialized via the queue, and non-async functions are only allowed with what we already know executing on the actor. However, self can also be captured by closures and local functions. Yes. So should those closures and functions have access to actor isolated captured self? Let's think about this ourselves. So if it's a closure, then it could be arbitrary code. So it should be treated as outside of the actor. It doesn't have the actor isolation privilege, right? Closure, we want to close out the bank account and distribute the amount amongst a set of accounts. So we get of accounts, and then for each, we get the transfer amount, balance, this is not safe, right? Yeah, it's accessing and modifying balance, which is part of the self actor's isolated state. Once the closure is formed and passed off to a function, we no longer have control over when and how the closure is executed. On the other hand, we know that for each is a synchronous function. Oh, it is not concurrent, so therefore it would be safe. Ah, I see. So if a closure is executed synchronously, then it is safe. If it's asynchronously, then it wouldn't be safe. Parallel for each, blah, 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 data race. All right. In this proposal, am I covering up part of the web page? Okay. In this proposal, closure that is non-escaping is considered to be isolated within the actor, while the closure that is escaping is considered to be outside of the actor. This is based on Parser's notion when closures can be executed concurrently. To execute a particular closure on a different thread, one will have to escape the closure out of its current thread to run on another thread, right? So if it's escaping, then it's not safe. The rules that prevents a non-escaping closure from also prevents it from being executed concurrently, right? To execute a closure concurrently, you need to first escape it. Therefore, a non-escaping closure cannot be executed concurrently. Therefore, it is part of the actor. Based on the above, parallel for each would need its closure to will be escaping. The first example for each is well formed because the closure is actor isolated and can access self.balance. The second example will be rejected by a compiler error. Partial application of non-async actor isolated functions like this is well formed only if it is the direct argument of a function to a function whose corresponding parameter is non-escaping. Okay. So in-out parameters. You can take a stored property and give it to a synchronous function via in-out parameters. But is zero form to pass them to asynchronous function via in-out. Okay, I think this is similar to the reasoning from before. If it's asynchronous, it has the potential to be parallelized, therefore it's bad. Yeah, so synchronous, okay. Asynchronous, not okay. This restriction prevents exclusively violations where the modification of the actor isolated balance is initiated by passing it as in-out to a call that is then suspended. Another task executed on the same actor then fail with exclusivity violation to try to access the balance itself. Okay. Escaping reference types. Yeah, this is the sad part, right? The rule concerning actor isolation ensures that access to a class stored property cannot occur concurrently, eliminating data races unless unsafe code has been subverted the model. However, the actor isolation rules presented in the proposal are only sufficient for value types. With a value type, any copy of the value produce a completely independent instance. Modification to that independent instance cannot affect the original and vice versa. Therefore, one can pass a copy of actor isolated stored property to another, even write to it in a into a global variable, and the actor will maintain its isolation because the copy is distinct. Sure, copies are fine. Reference types breaks this model because mutation to a copy of value reference type can affect the original and vice versa. So now we have a class transaction and we have an array of transactions. The transactions property is isolated, so cannot be modified directly. Moreover, arrays are themselves value types. So but the transactions stored in the array are reference types. The moment one of the instance of transaction from transactions array escapes, the isolation is lost. So you take if you return the most recent isolation, and then this code is escaped. Yeah, this value escaped from your isolation. At this point, the client can both modify the actor-based state by directly modifying the fields of isolation, because it's a freaking class, as well as see any changes that the actor has made to the transaction. This operation may execute concurrently with code running on the actor, causing race conditions. Bam! Not all examples of escaping reference types are quite as straightforward as this one. Reference types can be stored within structs, numbers, enums, and all that. So cannot look only at whether the type or its generic argument is class. The reference type may also be hidden in class, not visible user. Yeah, looks like a value type, but it's a private reference type. All right. So generics makes it even worse. Some types, like the standard library collections, act like value types. Right. So but it doesn't, as long as the generic parameter doesn't have any constraints, right? So then it could be either a value type or a reference type. So this is really unsafe. There are solutions, but the scope is large enough to deserve their own separate proposals. This proposal only provides basic actor isolation for data races safely with value types. Okay. Global actors. So global actor, let's see, revisiting it from my memory, from reading the roadmap, it's just this, you can mark global variables, and these actors can add tasks on them anywhere. So what we've described as actor isolation is part of the larger problem of data isolation. It's important that all memory be protected from data races, not just memory directly associated with the instance of an actor class. Global actors allow code and state anywhere be actor isolated to a specific singleton actor. This extends the actor isolation rules out to annotated global variables, global functions, and members of any type of extension thereof. Yeah, so this is what they mean by adding a new dimension for access control. Because now you can suddenly bound all these loose global things together and say this all are all actor isolated, right? So suddenly they have rules of which can be accessed and which cannot. For example, global actor allows the important concept of main thread, UI thread to be expressed in terms of actors without having to capture everything into a single class. Global actors provides a way to annotate arbitrary declarations as being part of process-wide singleton actor. A global actor is described as a type that has been annotated with a global actor attribute. Okay, so this is how you create your own global actors. Such a type can then be used to annotate particular declarations that are isolated to the actor. For example, a handler for a touch event on a touchscreen device. Yep. Declaration with a attribute indicating a global actor type is actor isolated to the global actor. Oh, interesting. The global actor type has its own queue and an own queue that is used to perform any access to mutable state that is also actor isolated with. Oh, this is a kind of radical. Wait, let me think. So suddenly all of these things can be asynchronous. Global actors are implicit singletons. There is always one instance of a global actor in a given process. This is in contrast with actor class, which there can be no instances, one instances, or many instances in a given process at any given time. All right. Detailed design. Actually, interestingly, the overview is longer than the detailed design in this one. A class can be declared as an actor class using the actor modifier. Each instance of the actor class represents a unique actor. All right. Actor class may only inherit from another actor class. Non-actor classes may only inherit from another non-actor classes. Actor class is like their own special thingy. own special class. All right. As a special exception described in the complementary proposal, concurrency interoperability with RWC, actual class may inherit from AS object. Oh, interesting. By default, the instance, class, properties, and subscript of actor class are actor isolated to the actor instances. This is true even for methods added retroactively on the actor class by extension, like other Swift type. So if you extend a actor class, the actor isolation extends to your extension, right? So you can define an actor class in one module, extend it to another module, import both module, call the extended method, and when you call it, you have to follow the same actor rule. So that means when you're calling an extension method, you'd have to call it within as a part of the isolation. So meaning you essentially call it within your extension of it. Of the actor class, I mean. Okay. An instance method, computed property, or subscript of an actor class may be annotated with actor independent or global actor attribute. If so, it is no longer actor isolated to the self instance of actor. Okay. By default, the mutable stored properties of an actor class actor isolate to the actor instance. A stored property may be annotated with actor independent unsafe to remove this restriction. Okay. Right. So in a normal class, right, a var is accessible as long as you have the correct visibility, right? It's internal, you can access internal, file private, whatever. But it is unsafe. It is not thread safe. So in the new world, where in the actor class, if you want to restore the same behavior of a normal class property, stored property, mutable, you'd have to explicitly say, okay, this is unsafe. But it's no worse than the normal class. All actor classes conform to a new protocol actor. Oh. That's new. I guess the conformance is synthesized by the compiler. Okay. The in-queue operation is a low-level operation. That's how the in-queue is actually, you can explicitly call it. Okay, and then there's a partial async task, has a function run that returns the value asynchronously. Oh, takes a async operation and returns the value asynchronously. In-queue requirement is special in that it only be provided in the primary actor class declaration. Cannot be final. If it's not explicitly provided, you get the default one. Okay, so this is how you implement your own queue and executor. Global actors. You create your global actor by marking your thingy with a global actor attribute. The type must provide a static shared property that provides the singleton actor instance on which any work associated with the global actor will be queued. type must provide a shared property. Okay. So this is the enshrining the variable name for singleton. It's like Swift has this attribute that marks something as a singleton and requires the existence of a shared singleton, and the name of that shared singleton is shared. Okay. It's pretty interesting. The custom attribute type may be generic. The custom attribute is called a global actor attribute. Global actor The custom attribute type may be generic. Custom attribute is called a global actor attribute. Global actor attribute is never parameterized. Two global actor attributes identify the same global actor if they identify the same type. Okay. So you can mark two global actor attributes. So you can make multiple identifiers. You can give multiple identifiers to the same actor, global actor. Okay. Global actor attributes apply to declarations as follows. A declaration cannot have multiple global actor attributes. Makes sense. The rules below say that in some cases a global actor attribute is propagated from one declaration to another. If the rules say that an attribute propagates by default, then no propagation is performed if the destination declaration has an explicit global actor attribute. If the rules say the attribute propagates mandatorily, then it is an error if the destination declaration has explicit global actor attributes that does not identify the same actor. Regardless, it is an error if the global attributes that do not identify the same actor are propagated to the same declaration. Okay. Propagation. A function, property, subscript, or initializer declared with a global actor attributes becomes the actor isolated with a group. Okay. So any kind of functions, essentially. Local variable and constant cannot be marked with global actor attributes. Okay. Type declared with the global attributes propagates the attribute to all of its members. Okay. An extension declared with global attributes propagates to all the members of the extension by default. Protocol declared with a global attributes propagates a property to its own conforming types. Oh, so you can use a protocol to propagate your global actors. Protocol requirement declared with a global attribute. You can declare a protocol requirement with a global attribute? Okay. Propagates the attribute to its witnesses mandatorily if they are declared the same module as the conformance. Okay, so far these may seem complex, but they are very intuitive once you realize what they're saying. A class described with global actor attributes propagates the attributes to subclass mandatorily. Overridden declaration propagates its global actor attributes to its overrides mandatorily. Okay. Other forms of propagation do not apply to overrides. It is an error if declaration of a global actor attribute overrides the declaration without an attribute. Okay. An actor class cannot have global actor attributes. Stored instant properties of actor classes cannot have global actor attributes. Other members of the actor class can have global actor attributes. Such members are actor class and not the global. Yeah, actor class of course is not global. It's an actor class. So its properties can't be that. Stored properties cannot have that, but other members may have that. And if the other members have the global actor attributes, then they're isolated by the global actors, but not the actor class itself. A D init cannot have global actor attributes. It's never a target for propagation. Nice. So these rules make it easy for a few classes and protocols to be annotated and be part of the global actor, the UI actor, for example, and for code that interoperates with these to not need explicit annotations. That makes sense. So UI kit, for example, can define some base classes, protocols that, and then take care of the entire ecosystem to make sure those code are executed on UI actors. And when you need to escape, you just mark your method to execute on a different actor. Actor independent declarations, you just mark them as @actor independent, like so. When used the declaration, it indicates the declaration is not actor isolated by any actor, which allows it to be accessed from anywhere. Moreover, interrupts the implicit propagation. Okay. Can be used on instance declaration in actor class to make the declaration actor independent rather than the isolated to the actor. Yes. When used on a class, the attribute applies to by default to members of the class and extension thereof. Oh, so you can use actor independent on a class. It also interrupts the ordinary implicit propagation of actor isolation attributes from superclasses. So you can prevent your class from inheriting the isolation by declaring yourself actor independent. All right. The attribute is ill-formed when applied to any other declarations. It's ill-formed if combined with an explicit global actor attributes. Makes sense. You can't declare yourself to belong to a global actor and actor independent. It doesn't compute. The actor independent attribute has an optional unsafe argument. When you use that, it's the same for the clients, meaning it can be used anywhere. However, the implementation is allowed to refer to actor isolated state. Okay. More escape patches, which would have been ill-formed under independent. Okay. Very reasonable. Isolation checking. Any non-local declaration in a program can be classified into one of 5 actor isolation categories. Actor isolated to a specific instance of actor class. This is the most straightforward. All the members of the class, right? Stored instances, computed instance properties, instance methods, instance subscripts. Yeah. Actor isolated to a specific global actor. Makes sense. Everything that can be marked actor independent. The declaration is not actors isolated to any actor, including properties, functions, methods, blah, blah, blah. Yeah. And independent unsafe. We literally just read about this. Okay. And then there's unknown. Declaration is not actor isolated to any actor, nor has it been explicitly determined that it is actor independent. Such code might depend on shared mutable state that hasn't been modeled by any actor, aka all the Swift code out there right now. The actor isolation rules are checked in a number of places, where two different declarations needs to be compared to determine if the usage together maintains actor isolation. So let's say when a definition of one declaration, for example, the body of a function, accesses another declaration in an executable code. For example, calling a function. So when you call a function from a function body, accessing a property, or evaluating a subscript. So this is in this scenario, we'll check the isolation rules. When one declaration overrides the other, okay, so whether you can override the other depends on whether you are isolated together. When one declaration satisfies a protocol requirement, okay, in order to, let's say you want to conform to a protocol and the protocol has a actor isolation, then you cannot declare yourself to be isolated by another actor, global actor, or that you're independent. Access is in the executable code. A given declaration called the source can access another declaration called the target in executable code by calling a function, accessing a property or subscript. If the target is async, there's nothing more to check. The call will be scheduled on the queue. Yeah. If it's async, is all good. Async in actor is all good. When it's not async, then the actor isolation category for the source and target must be compatible. Yes. Compatible means they're the same category. They're both actor independent. They're both actor independent unsafe, or they're both unknown. Very sensible, very intuitive. First rule is straightforward. Second rules means they are both independent, can use from anywhere because they aren't tied to a particular actor. Actor classes can provide actor independent instance methods, but because these actors are not actor isolated, that cannot read it. Because those functions, I believe this is a typo, because those functions are not actor isolated, they cannot read the actor's own module state. For example, in the extension of a bank account, we have a greeting that's actor independent. In this case, we can read our immutable stored property own name, but it cannot access the balance because balance is a mutable state that's actor isolated, right? So when you're independent, you cannot access it. Third rule is unsafe opt-out allows. So, okay, so because you said you're unsafe, then you can break the rules. Yeah, the fourth rule is for existing code. We all know that. Okay. Code with unknown actor isolation cannot back into isolated code, because doing so would violate the isolation guarantee of that actor. This allows incremental adoption of actors into existing code bases, isolating the new actor code while allowing them to interrupt with the rest of the code. Right. Yeah, so the ideal state is everything is actor isolated. Maybe with some part of it being actor independent because it may be convenience, right? And during your adoption, your migration, you may declare something as unsafe temporarily, but ideally this should never happen. Overrides. When a given declaration overrides another declaration, the actor isolation of two is compared, is well formed if they're the same isolation or they're actor independent. if this is absence, the overriding declaration will inherit the declaration. Right. If it's absent, then we'll just inherit. Okay. Protocol conformances. When a given declaration, the witness, satisfies a protocol requirement, the actor isolation of the two declarations is compared. The protocol requirement can be satisfied by the witness if they have the same isolation, if the witness and the requirement are async and unknown as far as actor isolations goes. Okay. The witness is actor independent and the requirement has unknown actor isolation. Witness is unknown. Oh, sorry. Witness is, okay, so protocol is unknown, meaning like a normal Swift protocol today. And then the witness is actor independent. Okay. Last one is important to allow actor classes to conform to existing protocols. Makes sense? We should all have synchronous requirements. Custom string convertible, for example. We can declare the description to be actor independent. Right. So okay, so because bank account is actor isolated, you cannot well, this computed property will have to be actor isolated. But that violates the check against the protocol because you cannot satisfy the witness. The witness must have the same actor isolation as the protocol, or the witness can declare a actor independent, therefore escaping its inherited protocol isolation. Okay, and we're done with this one. Source compatibility is additive. Nice. Woo! So, a lot of details in the actor isolation in terms of, because it's essentially access control. So there a new dimension as mentioned in the docs. And this is essentially establishing the relationship between this access, different level of access controls. Okay. And we're done with this one. The last one. This one is short as expected because it's about Objective-C. Okay, concurrency interoperability with Objective-C. You can try it out with this flag with the latest main snapshots. Swift's concurrency feature involves asynchronous functions and actors, while Objective-C does not have corresponding language features. What do you expect? Of course, asynchronous APIs are common in Objective-C, expressed manually through the use of completion handlers. This proposal provides bridging between Swift's concurrency feature and convention-based expression of asynchronous function in Objective-C. This is a very Apple thing. Only one company cares about this, unless you're a user. If you're a user, you don't care about that much because you get the APIs that just works. Trademark. Okay. It is intended to allow the wealth of existing asynchronous Objective-C APIs to be used immediately usable with the Swift concurrency model. Okay, I should say if you're also if you also have to use a lot of legacy Objective-C code, I guess this is helpful, right? Yeah. For example, consider the following Objective-C API in CloudKit. The CloudKit has a completion handler with our good old Objective-C syntax. This is just asynchronous, delivers the result via a completion handler. Direct Swift translation is very similar, slightly shorter. Existing Swift code can call this API by passing the closure to the completion handler. This proposal provides an alternative Swift translation to async function. So this is really benefit example because it makes the API nice to work with. Even though we already saw there's a continuation thing that you can use to bridge the two worlds. So this technically can work with the async APIs, but instead you can use this. So this argument that the completion handler takes now gets directly, quote unquote, asynchronously returned. And the error, if it has an error, then the error gets thrown instead. Yeah, motivation on Apple platforms is important. Objective-C API is an important part of the developer experience. There are many ways you interact with it, and then there's many mentions of Apple's SDKs. So the solution, without actually reading it myself, right? Solution is essentially we use the importer to transform all these calls, do some pattern matching, and in some cases directly look up the definition and map it to a different definition. Okay, translate completion handler methods to async calls in Swift. Allow async methods defining Swift to be Objective-C so that you can be called by Objective-C code. Okay. Provide inference rules for asynchronous handlers. Provide attributes to tune the translation. Okay, obviously, so they actually are updating Objective-C itself so that you can annotate the code, right? Control over how completion handler-based APIs are translated to async functions. Specify when Objective-C APIs as part of the particular global actor. Specify when Objective-C APIs. Okay, so calling back to the coordination of this whole project within Apple, this is another part, right? The team that works on Objective-C now have to introduce all these new attributes, and all the framework owners now have to use these attributes to make their APIs concurrency friendly. The detailed design section describes the specific rules and heuristic being applied. However, the best way to evaluate the overall effectiveness of the translation is to see its effect over a large number of Objective-C APIs. This pull request demonstrates the effect of that proposal has translates. Oh, let's take a look. 5,000 line additions. So interestingly, instead of replacing the old API completion handler, they added a new one. I guess that makes sense, right? You need to maintain code compatibility. Yeah, so many functions I've used can use it. Because I feel like application development especially is async by default. Not a lot of things are synchronous when it comes to interacting with the system. When you write your own code, of course, like when you're serializing some models or something, those are easy, simple enough to stay synchronous. But when you're trying to put pixels on a screen or get data from the network when you're interacting with your environment, you have no choice but to be synchronous. So asynchronous. So all these system APIs are all synchronous. Sorry, asynchronous. Anyways. Okay, detailed design. Obsessive method is potentially asynchronous completion handler if it meets the following requirements. Has a completion handler parameter that receives the result of asynchronous completion. It must meet the following additional constraints. So this asynchronous handler itself returns a void, called exactly once. If it delivers the error, then one of the parameter must be NS error, and it has to be non-null. And when the error indicates there is an error, the error occurred. The method itself has a void result type because all results are delivered by the completion handler. Yes. So this is like asynchronously returning a result. Yeah. So if you're returning like a true or false, then we can't do the automatic translation. So this kind of async completion handler method will be translated into an async method when it's either annotated explicitly with an appropriate Swift async attribute, or it is implicitly inferred by the following heuristics. Okay, so we're just essentially reading some code in the client importer described in English. All right, let's go. If the method has a single parameter and the suffix of the first selector piece is the phrase with completion. Aha. With completion handler, the sole parameter is the completion handler parameter. The matching phrase will be removed from the base name when it's imported. If the method has more than one parameter, the last parameter is the completion handler parameter. If its selector piece parameter name is completion handler, or with completion handler. Okay. When the completion handler parameter is inferred, the presence of an NS error that is non-null, completion handler block type indicates that the translated method can deliver an error. Okay. The translation follows the normal translation procedure with the following alterations. Completion handler parameter is removed. Of course, completion handler, the whole point is to remove it so that it can asynchronously return it instead. If it delivers an error, it is thrown, in addition to being async. The parameter type of a completion block handler, the parameter type of the completion handler block type are translated into the result type of the async method. Makes sense? Subject to the additional rules. Okay. If it can deliver an error, then it's ignored. Makes sense? If the method can deliver an error and a given parameter has non-null result qualifier, it will be imported as an optional. Okay. Oh, nullable result. Sorry. Yes. So optionality gets ported. If there's multiple parameter types, so multiple parameter types is no problem. Just become a tuple. All right. So here's the example. We can see a lot more example from that pull request. Yeah. So if you really are interested, you should look at this without the answer and perform these heuristics and see if you get the same result manually. And this is how you use it in the new world. Yeah, and this actually uses the continuation API to demonstrate how it's translated. With unsafe continuations. Yeah, with unsafe continuations. Additional rules applied when translating the Objective-C method name into a async function. Some words are removed. Yeah, get is removed. Asynchronously is removed. Nice. Okay. So your Swift method gets translated into Objective-C signature as well, and I assume that's going to be more regular, right? Perform with operation, completion handler. You see, like if I still write Objective-C these days, this will provide some guidelines of how to name your stuff, right? So that will become this, and this one becomes async throws method. I assume we'll just like tuck in the error as part of the completion handler's argument. Yep. The synthesized method implementation will create a detached task. Okay. Perform dangerous trick. So synthesized by the compiler, it will become run detached, await, and complete. So this is how Objective-C will call your method. Okay. Actor class can be Objective-C and will be available in Objective-C as other classes. Require their superclass, if there is one, also be an actor class. However, this proposal loosens that requirement slightly to allow actor class to have NS object as a superclass. This conceptually is safe because NS object has no state and makes it possible for both actor class to be Objective-C and also implies conformance to the Objective protocols, which is required to. Okay. Member rank can be only Objective-C if it's either async or outside of the member of an actor class can only be Objective-C if it's async. Okay. It is outside the class's isolation domain. Okay. Isolation domain. Okay. This is the first time this is called isolation domain, but it makes perfect sense. Synchronous code that is within the actor's isolation domain can only be invoked on self. In Swift, Objective-C does not have knowledge of the actor isolation, so these methods are not permitted to be exposed. So synchronous code can't work. Asynchronous is fine because we're sending a message anyways, right? If you're independent, it's okay. If it's async handler, yeah, async handler is a new thing. Inference of async handler. Async handlers are synchronous functions whose body executes asynchronously. The async function attribute can be applied to a requirement of protocol and will then be inferred from a method that satisfies the requirement. This allows one to easily use asynchronous constructs when receiving synchronous callback that requires no immediate action. Objective-C delegate protocols often use did methods to report on action that occurred, but doesn't necessarily need an immediate response. For example, the collection view delegate contains the view did methods such as did highlight item at index path. For Objective-C protocol method with the word did in the name, either anywhere in the first selector piece at the start of the subsequence of selector piece that meet the form required by async handler, void return, no in-out parameter, etc. The async handler attribute will be inferred by the API. So it will become something like this. Completion handlers must be called exactly once. The Swift async function will always suspend, return, or produce an error. For completion handler APIs, it is important that the completion handler block be called exactly once on all paths. This is talking about your Objective-C code, including when producing an error. Failure to do so will break the semantics of the caller, either by failing to continue or executing the same code multiple times. While this is an existing problem, widespread use of async with incorrectly implemented completion handler API might exacerbate the issue. Yes. So recall that when you are importing an async Objective-C code, it uses the with unsafe continuation API, and continuation needs to happen exactly once. So if your completion handler gets called multiple times, then the continuation thingy gets called multiple times, which violates the precondition of that thingy. Okay. Fortunately, because the compiler itself is synthesizing the block that will be passed to completion handler APIs, it can detect both problems by introducing an extra bit of state to the synthesized block to indicate that the block has been called. If the state is already set, the block will be called, then it has been called multiple times. If the bit is not set when the block is destroyed, then it has not been called at all. While this does fix the underlying problem, it can at least does not fix the underlying problem. It can at least detect the issue consistently at runtime. So we resolve to some runtime heuristics to provide a little help. And then we have a bunch of annotations that helps you make your Objective-C APIs nice Swift APIs. Okay. Yeah, so as regards to source compatibility, we saw it in the pull request. Instead of replacing the existing callback APIs, that API now gets translated into two separate APIs, one async version and the original version. So lookup with completion handler will become lookup name with completion handler, as well as lookup name async returning a string, right? So this is interesting. This is the new URL session API. Is this always uppercase? That seems wrong. Okay. Overall, I'm less interested in Objective-C. So this part, I skimmed it. Okay. So where does that land us? We have read in 5.5 hours all the proposals as well as the roadmap that links to the proposal. I feel like I have absorbed, let's say 85% of everything. Oh, maybe 90%. Yeah. Conceptually, I understand everything that gets introduced. I feel like being on stream forced me to examine what I read out loud and ask myself if things make sense, and having to explain it to myself and to potential audience also helped a lot. Yeah, because when these things were coming out, was it yesterday? Yeah, I tried to read them in silence, and I just stopped after a while because it's just a wall of text, and it required a lot of concentration. So, I guess what I'm saying is this has been very helpful to me. And who knows, maybe someone will enjoy watching this. Yeah, and I do think, watching me reading out loud and work through all these things is preferable to a lot of people than reading it. I have a sample of one. Like, I'd rather watch someone work through this than reading through them. Except my hack here is I recorded the video. So yeah. So hopefully someone will like this. Yeah. Gilad thinks it absorbed 40%. It's much better than 0%. Thank you. Yeah. That's the downside, right? Like, with this much information, with this many hours, it's kind of hard to watch in one go, let alone in real time. Yeah, totally understand. Okay. And I really need to eat. I haven't eaten anything today. So I think it's time to call it. Yeah. Thank you very much for watching, everyone. And if you're watching this on YouTube in the future, please give the video a like, subscribe to my channel. I have some really good stuff coming out. Hopefully they'll come out. I'm very excited about them. And I'll see you next time.